the recording is on. All right, so I'll share my screen and then we deal with the first thing in motion, which is the sets. So from 11 to 12, we're going to be dealing with sets and functions, and everything Professor Halloward Olaoluwa has taught us. That's what we'll be breaking down. But we'll be breaking it down in our own terms, in our own simple terms. All right, that's what we're breaking down into. So just tell me, I'm sharing my screen now. Tell me if you can see my screen. So it's the same course material, right? And I'll be breaking it down. Yeah, it's the same course material we're going to use. We're not going outside the course material. We'll use the course material. We'll explain everything in the course material. If you have questions, if you have, um, ideas, we're studying together as students, as youths, actually. So just, yeah. All right, let's start. So I will be switching tabs. Sometimes I would share. I will be switching tabs. When I want to make more explanations, I'll go to the board. This is the board I'm going to be using. I'm going to be using the mirror board. So I can type questions. I can type questions in here and I can solve. It's just as if we're in class. So it's as if we're going to be in an interactive class. Okay. So that's how it's going to be. And we'll get it. So let's get to business. All right. Sets and functions. And Mr. Holloway told us the learning objectives. He said using Venn diagrams, which is something that is very vital and something that we need clarity on, explanations on. And don't worry, most of the terms he used in class, most of the terms he used when he was taking his lectures, I teach American students as well. So most of his terms are US standard, right? He was bringing in US standard, giving us those grammars he was speaking were US standard. So we might not really understand, okay? So I think Miva is using part of US standard and their curriculum as well. So let us deal with what's at hand. Now, operations on set, okay? So we have operations on set. Then he talked about the universal set, and there was no much explanation on the universal set, but I'll give a brief on that universal set so we can have clear understanding on the universal set. So let's take, for instance, we have, 1 second. So let's take, for instance, I'm sharing my board now. So let's say we have, this is it. Let's say we have this. Let this be a circle and this be another circle. Let's call this A and let's call this B. So you can see my interactive board. I actually use my hands, to draw, so don't mind my drawings. So let's call this A and let's call this B. And let's say in set of A, let's say that A has some numbers, which is 1, 3, and 6. And let's say B has some numbers, a set of numbers, which is, let's say, 5, 7, 3, and 6. So the union of both of them is going to be like a combination. So what we're doing is we're adding everything together. We're putting 1 in A, 3 and 6 both appear in A and B, so they stay as an intersection. Then we have 5 and 7. So when you say the union of everything, you mean like the union of the entire set. The union is actually represented by a sign like a U. All right, it's just like this. This is union, okay? So it's represented by a sign like a U. And when we say the union of the set, we just mean 1, 3, all the set numbers that is there. 1, 3, 6, 5, and 7. 1, 3, 6, 5, and 7. So that's actually what it means for union. Now, when you talk about intersection is just like the end shape, okay? Hot mic, hot mic, hot mic. So intersection, please, can you help mute your mic? Okay, so intersection is just like the end shape. 1 second, I think someone's mic is on. All right, let me just mute it for the person. Okay, so When we talk about the intersection, we just mean the things that are common. So we have 3 and 6 that are common there. Okay. Now, he was talking about the complement. Now I'm going to break down everything that we need to learn or we need to know about the set. So please pay attention. Don't worry, it's not going to take much of our time. Okay, so please pay attention. The first thing we want to understand is that set now, according to this explanation, just a collection. All right, so it is a collection of objects. Now, these objects could be numbers, things, it could be places. All right, so generally speaking, the above definition is that is a collection of objects. Set is a collection of well-defined objects. All right, so let's get down to the main things. The first thing you want to understand is universal set. So whenever they're talking about universal set is like the mother of all sets. Most times it is usually outside here. Most times it is usually outside here. And what it is telling us that it is comprising of everything inside the set, both A, both B, both the one that is outside. Let's say we have 8 and 9 outside, everything that is inside the set, okay? It is comprising everything together. So that is what universal set is. So the universal set is the mother set from which other sets emerge or they relate to. So I'm going to be quick. For instance, let's say we have a universal set and we say that all SS3 students or all Miva students of Lagos State. And let's say this is our universal set. Okay, so this is universal set. Why is Lagos so hot? So this is universal set, and I'm putting this one as, let's put it as all Miva students. So say all Miva students in Lagos State. All right, so that should be our universal. And then let's say that A is for students of software engineering, and B is for students of cybersecurity, and let's say C is for students of, let's say, public health. Okay, so let's put it this way. All right, so A for software engineering, just going to put SD, software and developing the software engineering department. Then let this be CD. Okay, let's not take it the other way. Cybersecurity department, and let this other one be public health department. All right. Now, as long as we can find A, B, C in the universal set, because it comprises of all Miva students in Lagos State. So it doesn't matter about your departments and all that. So it doesn't matter about the department, you're all in the universal set. And that's what universal set means. That's what it means. So right here now, before I move into power sets and the likes, okay, so right here, we're able to explain universal set. It just comprises of everything. Don't worry, we'll soon get into the laws and we'll also get into more questions. When we get to Venn diagrams, that's when you start enjoying the questions, and we'll get there in 10 minutes. So the universal set here comprises of everything. Then we have the intersection, which comprises of what is common in both sets. And then I just told you what universal set is with an example of Miva, all Miva students in Lagos, and we have software, engineering department, cybersecurity, and public health. So do we have any questions in this before we move into power sets? Any at all? If we can move on, you can just put a thumbs up and we'll move on. All right, thank you. Let's move on. All right, so let's discuss about power set. So we've been able to explain the intersection. We're able to explain the union. Don't worry, I'll talk about power sets, and then we'll come into complement of sets, because these things you actually need to go step by step before you just jump into the complement. But let's deal with power sets first. So let's talk about power sets. Sorry. Let's talk about power. So whenever we're dealing with power sets, don't mind my handwriting now. Let's talk about power sets. Now this is a collection of all the subsets in a given set. Okay, all the subsets in a given set. So now let's say I have set A, and my set A, let's say I have set A. Sorry, let me share my board. Let's say I have set A, and my set A comprises of 1, 2, 3. So these are the elements of my set A. Now, if I want to list the power sets will be equals to, this is how you find power set, just in case you're asked anywhere. The power set is equal to, is denoted by 2 to the power of A. What do I mean? Whenever you're dealing with the power set, you have to just raise it to, you just say 2 to the power of that set. And there are how many elements in A? There are 3 elements in A. Now, forget that I wrote 1, 2, 3. What if I can put it as this? I can put it as 5, 7, and 8. And they are all the same. Okay, they are all the same. This is telling us that there are 3 elements in the set A. So forget the 1, 2, 3. Okay, there are 3 elements in set A. So my power set is telling me that this is 2 to the power of 3, since there are 3 elements in set A. And 2 to the power of 3 means 2 times 2 times 2, and that is 8. Meaning there are 8 subsets. So the power set is actually going to give us how many subsets we can find in that set. So meaning there are 8 subsets. All right. So what do I mean by subset? Subset means, like I explained, subset means that things that are part of a set. All right. Look at this universal set we have here, the one with the universal set. A is a subset of the universal set. B is a subset of the universal set. This 8 and 9 that is outside is also a subset of the universal set, even if they are not defined. Okay. So that means we can represent this A in 8 subsets. The first subset you want to know is the empty set. Empty set is denoted by an empty bracket. So we can have it like this. This is empty. You can put empty subset like this, or you can just denote it like this. This is empty. So when we talk about let's use just one sign. So the 8 subsets, first of all, every subset can be empty. So we have the first one as an empty set. Another way we can represent A like this: 5, 7, and 8. The entire thing, we can put it like that. So 5, 7, and 8 is also a subset of A. And then we can also represent it as, we can say 5 itself, just 5, is a subset of A, right? 5 is also a subset of A. Then we can also say that 7 is a subset of A. 7 is also a subset of A. We can say 8 is a subset of A. Help me count, because it is the mathematics told us that it's only 8. Then we can say 5 and 7 are subsets. We can also say 5 and 8 is also a subset. 5 and 8 is a subset. And then we can say 7 and 8. So I think we've touched everything here. So let's count. There are how many here? We have 1, we have 2, we have 3, 4, 5, 6, 7, 8. So there are 8 subsets in just A. We can derive 8 subsets from A. And that's what the equation of power sets gives to us. It's like you listing the elements in a set. It's just like that. Okay, it's as simple as that. It's like you listing the elements in a set. All right, so now that we have that clear understanding, let's go to what we call the equal sets. Okay, so some people will be asking or wondering, what is equal set and all that? Okay, we have 5 minutes before we get to complements, and then the next 5 minutes we start touching the laws. All right, so some people will be wondering, what is equal sets and all? So for instance, let's say, let me use this part. Sorry, let's use a black. So let me use this part. Let's deal with the equal sets first. So you might be wondering what is equal set. So let's say if let's say x itself, right? Let's say x is equal to a b c d, a b c d. All right. So x equals a b c d. Let's say y is equal to, let's give y its own. Let's say b d. Let's say b d a c d. And let's say k is also equal to a b c d e f. All right, so let us understand. Let's put another one. Let's say z is equal to a b c d, or you can say the first four letters of the alphabet, but let's just say a b c d. Okay, so now we can say that x is equal to y. Look at this. We can say x is equal to y. This is how we derive our equal set. X is equal to y because we have the same element. Now, look at, I know you're seeing d and d. Yes, but it is counted as just d. It is read as just d, okay? So it's the same element. So we can say that x is equal to y. So we have the same element, all right? So x is equal to y. We have a, b, c, d. And the same thing in x, a, b, c, d. So x is equal to y. They contain the same elements when counted once. So b in repetition is just 1. Then we can also say x is equal to z, set z, because they're also having the same thing. All right. But x is not equal to k because k now has e and f. So this is what we mean by equal set. All right. This is what we mean by equal set. Then we have what we call the equivalent set. So there is a difference between equal set and equivalent set. Now it might be confusing, huh? Yes. For equal set, let's get to equivalent sets. Then I'll show you. You'll be able to derive the difference yourself. Let me just put that margin. So this is how equivalent set is. So let's deal with equivalent. So let's deal with equivalent sets. Sorry, I just had to. Now for equivalent set, it is quite different. For equivalent set, it is telling us that let's say we have A equal to set 1, 2. Don't worry, we're getting to the interesting part of sets where you learn the formulas and the laws. So let's say 1, 2, 3, 4. And then let's say we have B equal to A, C, D, E. And let's say we have C equal to, let's say set C is A, B, B, E, C, D. A, B, B, E, C, D. All right. So now we can say that A is equal to B. A is equivalent to B. Why? A is equivalent to B because they have the same number of elements. So equivalent sign is denoted like your hamburger. It's like this. This is the hamburger for the equivalent sign. So A is equivalent to B because they have four elements. A has 4 elements inside of it. B also has 4 elements inside of it. But A is not equal to B because the element inside A is different from the element inside B. So A is 1, 2, 3, 4, and B is B is an alphabet, A, C, D, E. So it is not equal, but it is equivalent because they have four elements. Do we understand that part? All right. Okay. So they have four elements. Now, that's how we denote what is equivalent. Now, neither A nor B is equivalent to C because C has a sixth element. C has a sixth element and it cannot be paired. So, but we can say that B is equal to C because the elements in B is the same with the elements in C, but they're not equivalent. All right. Now that you have that understanding, that is the difference between equal sets and equivalent set. One has a hamburger sign, which is the equivalent set. The other has just equal to sign, which is the equal set. Okay. One is talking about the numbers of elements inside of it, like the equivalent set. A has 4 elements and B has 4 elements as well. So they're equivalent. The other is talking about the elements itself. So are they equal? Like B has A, C, D, E. C also have A, C, D, E. The same thing. So they're equal. Now, we then move into, we've talked about union, we've talked about intersection. That is something that is common. Okay. So now we then move to, there are other set notations like the element of, things that are denoted. For instance, let's say, let me break it down. Okay. All right. So let me break this down. So there are other elements like this is denoted by. Okay. So let's say this means an element of. Okay. What this means is element of. Okay. My handwriting is getting a bit. So that means element of. All right. So let's say y is equal to is given the set of x such that x represents numbers between 10 and 15. So we can as well say numbers between 10 and 15. We can as well say 11 is an element of y. Okay, we can say 12 is an element of y. Okay, we can say 13 is an element of y. But we cannot say 30. 30 is not an element. 30 is not an element of y. So you see that? So those are other set notations. We also have something called cardinality. Something we should also, so this is cardinality of the set. All right, I can see. All right, yes, Mr. Yusuf Abdullahi. You have a question?
Yeah, I have a question about this that is not a elements of y. So is it these elements? It's not what it is not being at like from the 11 to 19, not the 20 up to 30.
Yeah, we're going to define, thank you, Abdullahi. We're going to define it by what is given to us. So what is given to us is y equals x, and x is representing 10 numbers between 10 and 15. So
Okay.
yeah, it comprises of only this set of numbers. So that is from 10, 11, 12, 13, 14, and 15. Do you understand?
Oh,
Yeah,
I
so
understand.
numbers between, yeah. So 30 is outside that range of what is given to us or what is defined. So 30 is not in this definition now. 30 does not belong to Y. It's not an element of Y.
Okay, sir. Thank you.
I'm not Sao, I'm your fellow student, please. My name is Gideon.
Oh, so like
All
sir,
right.
between you and two by now.
Okay. Thank you. Let's go to cardinality.
Okay, sir.
Okay.
I'll repeat again, sir.
All right. Thank you. You have another question, Yusuf, or you're clear? Okay, I think Yusuf is clear. So I'll just lower the hand. All right. Now let's go to cardinality. Now, cardinality of set refers to the number of elements in the set. That's cardinality. Number of elements in a set. So now let's take this. Let me just write it down so we get it clearly. Don't worry, everything on this board is also recorded. It doesn't go anywhere. So if you need what we've done on the board, I can still send it to you via your email. If you need what we've done in the class, it's recorded as well. So the number of elements in a given set, that is cardinality of a set. Okay, so that is cardinality of a set, number of given elements in a set. Now let's say X. Let's take, for instance, X is given as, sorry about the red. So let's say X is given as ABCD, for instance, ABCD. Okay. All right. Yeah, if I'll send that. So let's say X is given as ABCD, and we want to find the cardinality of X. We just say cardinality is denoted by just a small letter n. That is number of elements. Then insert X is equal to, all right, Chidima, is equal to what? 4, because there are 4 elements inside. Okay, there are 4 elements inside of X. So if we have Y equal to, let's say, A, B, C, D, E, F, we say the cardinality of Y. We say the cardinality of Y is what? Cardinality of N, that's NY, will be equal to what? 6. Because there are 6 elements in Y. That's how we deal with cardinality. So those are other set notations. We've talked about, so far we've talked about equal set, we've talked about equivalent set, we've talked about the element of using set notations, we've talked about the cardinality of set, okay? We've talked about the union and intersection of sets, we've talked about power sets and how to derive your subset, telling you that empty sets are also subsets. Now, let's go into complement of set. Before we move into complement, do we have any questions? Okay, so let's go into the complement of set. So before we move into complement, there are no questions? All right. So now let's talk about complement. What is complement? The complement of any set, all right, is the set that has every element in the universal set except those that particular set. So let me go back to this. Let me use a fresh example. All right. Complement is actually denoted by, sometimes you see it as, we see our complement denoted as X, they call it prime, or you can see it as X complement, like this. So you can put it like this. This means the complement, or this also means the complement. Whichever way it is written, that's how you just define it. All right, so let's say we have U. Let's say we have an example. Take this aside. Let's say we have our universal set, or let's say we have U, and let U be equal to 10, 20, 30, 40, and 50. All right, 10, 20, 30, 40, and 50. So let's say U is equal to that. And then let's say Y is equal to just 20 and 50. So to find the complement, we do what we call a subtraction. Now, I'm sure you saw that in your test where they told you to subtract some set numbers. You know, the mistake most people will make is go and subtract the elements of the set with the other one, which is quite wrong. What we do for that subtraction is we remove any elements that is there. Don't worry, I'll show you what it means. To find y complement or the complement of y, what we do is we say the universal set minus the set of y, and this is how it's going to be represented. So we know the universal set as 10, 20, sorry, it's okay. So we know the universal set as 10, 20, 30, 40, 50, and 50, right? So this is universal set minus the set of y is just 20 and 50. So what you do is that you just eliminate, when you're subtracting sets, eliminate what is there. What you're going to be left with is the y complement will just be what? 10, 30, 40. Do you understand? So you don't, okay. Okay, thank you. So you don't actually subtract the values. What you do is you just eliminate. Yes, Genevieve.
You said we should eliminate the elements in what in both complements. So how did you get y complement is 10, 30, and 40 since the y is 20 and 50 and we already eliminated all the elements in y. The other 10, 20, 30, 40, 50 are they not supposed to be the element in x complement?
All right, thank you. So what we're looking for is a y complement, right? We're giving
Mm-hmm.
just the set of the universal u, and we're giving y. So to get y complement, let me break it down with this English. It's just what does what does set of y have that you can exclude from the universal set? That is y complement. When we eliminated 20 and 50, we were left with 30, we're left with 10, 30, 40. That's the meaning of y complement. Right? Okay.
Mm-hmm.
So what is it that when we finish eliminating, what is left? That is what complement means.
Oh,
Yeah.
yeah. Thank you.
You're welcome. All right. So now you have a clear idea and understanding of what complement is. So we're moving into laws now. Okay. Yep. We're right on time. We're moving into laws of set. But before we go into laws, let's talk about what is disjoint and non-disjoint, because I think it popped up in the test quiz. So let's talk about what is disjoint and okay, disjoint and non-disjoint set. So now a disjoint set, let me put that here. A disjoint set, let's say we have two sets. Two sets are disjoint when they have nothing in common. So let's say we have a set of x to be equal to 5, 6, and 7. And let's say we have a set of y to be equal to 1, 2, and 3. They might be equal, but they're disjoint. Disjoint is telling us that the intersection of both sets, remember intersection, what you can find common, the intersection of both sets is an empty set. So we don't have 1 in x, we don't have 2 in x, we don't have 3 in x, which means it's a disjoint set. Now, we now have what we call non-disjoint set. also popped up in the test. So non-disjoint, that's why I have to touch it. Non-disjoint set is stating that what? The sets they have at least one thing in common. So let's say we have set A to be equal to 5, 7, and 9. And let's say set B is equal to 5, 4, and 8. So this is a non-disjoint set because, okay, sorry, this most times they represent sets in a capital. So let me just, it's a non-disjoint set because A intersects B is not an empty set. A intersect B is giving us something, it's giving us 5 because 5 is common in both of the sets. That's the difference between disjoint and non-disjoint. At least one is common in non-disjoint. Now we'll move into laws of set. In laws of set, we have 7 laws, 7 good laws. There is the first one we have is the idempotent law. And we'll explain it because let me touch that part very well. Because these laws actually got confusing in one part. So let's move over to what we have here. So we've actually touched the complement, we've touched intersection, we've touched union. Let's move forward. We've touched the difference in sets. Okay, we now understand how you eliminate sets. Remember when when we did this, how to find the difference, we just eliminated what doesn't belong, right? So we've touched that part, the difference in set, and the union of the set also. That means it just comprises of everything altogether. That is the union. And then, okay. And then, okay, he gave examples as well. That for difference of set. So this is something now that you have a clear understanding of, you can deal with. All right, so now the laws of the set. The first one we have is the idempotent law. Well, he called it the idempotency. In Nigeria here, we just call it the idempotent law. Well, for US, they expand it because some of their curriculum actually gives this. What we call expansion here, or what we call open the brackets here, is called distribute in their side. So there are so many English that are different from ours. But let's break it down. All right, so for the idempotent law, it is stating something in common. It is stating that if there are two sets, okay, idempotency law is telling us that A intersects A, which is the same set, and A union A is just A. So idempotency law, if you look at this closely, just this part you see here, idempotency law is telling us that everything that belongs to A should be of A, and everything that belongs to B should be of B, and everything that belongs to C should be of C. That's what it's saying. So this is how the laws are written. Let's go into laws of sets. So this is how the laws are written. Sorry about that. I think I lost my connection for a second. Just connected back to the Wi-Fi. So, what was I even explaining? Okay, yes, this. Okay, so I said A to the union of A is just A, and then A intersect A. A intersect A is still A. So for the idempotency law, right, we call it the idempotent law. That's what we call it. For the idempotent law, okay, everything that belongs to A in a set. Sorry about my circle. Why is my hand not straight? Let me use a circle instead. Okay, good. Anything that belongs to a set of A must belong to A. So I don't care if they write it like this or like this. Everything in A belongs to A. That's what the idempotent law is saying. Now we also have what we call, this is idempotent. So let me just put it here. Or whichever way you can pronounce it. But that's how I pronounce mine. Then we have what we call the associative. So the associative law is telling us that if we have A union, A to the union of, that means when I say union, remember it's everything combined or comprising of everything, okay? So A union B, any questions? One second, please. All right, I'm still with you. So if we're having, let's say, A union B union C, what does that mean? A union B union C. So let's say I have a circle like this. I have A, then I have set B at this side here. 1 second. Okay. I have set B at this side here. So let this be set B. All right. So, and then I have set C. Let set C be here. Okay. Let this be C. Let me just put one here and one number here. Okay. So A union B union C. So it's equal to, for the distributive, it is equal to, it's the same thing as saying A comprising of everything of B in one side, which is still comprising of everything of C in another side. So associative law is quite, well, anything union now just means everything all together. So we're going to have 1, 2, 3, 4, 5. When you say A union, B union C, automatically B union C is 1, 3, 4, and 5. Okay, look at B union C this way. 1, 3, 4, and 5. So if we say A union B union C, we just add everything all together. 1, 2, 3, 4, and 5. Hope that didn't confuse us. Are we clear on that? Did that shake us a little bit? Okay, we're good. Now, also in the, okay, thank you. Now, also in the intersection, all right, A intersects B. In the intersection, we can say A intersects B intersects C. And for A intersects B intersects C, we have, it means that we're going to distribute it like this. A intersects B, then intersects C. So what that means, intersection is what is common in both of them. So what is common in A and B is 3 and 4. what I'm sorry, what is common in A intersects B is just 3 at this side here. Okay, then if we put it with the intersection of C, we have 3 and 4, because this 4 is also contained in C. So what is common in both A and B is just 3, and then what is common in with C is 4. So we have 3 and 4. That's how we read it. Okay, then now this is what we call the associative law. We can also relate the associative law in maths when you're doing your common expansions. You can actually refer to that in mathematics. So there was actually one he asked question of in the test that most people made mistake of, which is the Morgan's law. We're coming to that though. We're coming to that part. Okay, so let's say I have, so let's go to the commutative. So commutative law. Now for the commutative law, we have, for the commutative law, we have A union B. Okay, let's watch this. We have A union B. Commutative law is just trying to tell us that things might actually be the same, or things might actually look the same. That's what commutative law is telling us. Things might actually what? Look the same. 1 second. So it is telling us that things might actually look the same. So if we have A union B, A union B means B union A. Just like you saying 2 times 3. 2 times 3 is the same thing as 3 times 2. And A intersects B. In commutative law, is the same thing as B intersects A. That is how commutative law reads. So if I have A union B, what I have here in A union B is 1, 2, 3, and 4. B union A, the same thing, 1, 2, 3, and 4 at this level here. If I say A intersects B is just 3. And B intersects A is still the same 3. So they are commutative. That's how commutative law is. Okay. Then we have what we call the distributive law. We have what we call distributive law. And as for the distributive law, it's just we of a distribution. Yes, Yusuf.
Okay. Can you hear me?
Yeah, I can hear you.
Okay. Apart from this commutative law, I can't understand what you mean for this in these sections.
Okay, you don't understand the associative and idempotent.
Commutative law.
Okay,
Yeah.
commutative. All right.
Yeah.
So for commutative now, we're saying it's just like you saying 2 times 3 is the same thing as 3 times 2. Right?
Okay. Yeah.
So if we say A union B is everything that comprises A and B together.
Okay.
So which is 1, 2, 3, and also 4.
Yeah.
Right? The same thing if we say B union A, it's still the same thing. 1, 2, 3, and also 4.
So I look.
Yeah.
Let's look like A is true, B1, 5 is C. So in this section from 3 and 4, that is why for confused for this thing.
Oh, okay. All right. So in the section 3 and 4, 3 is also part of A, right?
Okay.
And 3 is also part of B.
Okay.
4 is also part of A, B, and C. So it belongs to A and B as well.
Okay, that is why for encircle it, for anyone
Yes.
we interact with each other.
Yes. Exactly.
Okay, I understand.
All right.
Okay.
That's all right. That's great. So let's move into the distributive law.
Okay. Go ahead.
All right. Let us talk about distributive. Now, for distributive law, you can say A intersect is just like you distributing. In US, they call it distributing. In Nigeria, here we call it expansion of bracket, or we say expand the bracket, open the bracket. You know, that's what we call it in Nigeria. Over there, they say distribute. So A intersect B. Let's say we have A intersect B union C. So what this means for distributive means just follow the pattern. It means A will intersect B and A will also intersect C, just like you opening the bracket. That's how distributive works. So if I'm to distribute this, this is going to give me distributive law. This is going to give me something like this. This would be A. This would be A intersect B, and then union A intersect C. That's how it's going to be like. A intersect B, and then union A intersect C. That's how it will be for distributive. So if I have A union B intersect C, what this is going to give me would be, I just distribute, remember the pattern, distribute, that would be A union B and A union C. So this would be, sorry, this is going to give me A union B, just like you opening the bracket, intersect A union C. This is like you opening a bracket. So let's play with it with normal math. If I have 3 into parentheses, x plus y, and I want to expand this bracket, what I do is I open the bracket using 3 to multiply everything inside. So this would be 3 times x plus 3 times y, which is 3y. And it's opened, it's distributed. That's how we deal with it. Okay, so that's just an example of what the distributive law, what it talks about. Then let us move into that law, which is called the De Morgan's law, the one that got us confused in our test and in the question. Now, when he explained De Morgan's law, this is De Morgan's. Okay, out of respect, let me make his name capital letter. De Morgan's law. So, De Morgan's law is telling us something. What if we have A union B complement? So everything in A and everything in B complement. What this is saying, it means that this is just going to be like the distributive law, it's just that the sign will change. So what this is saying is A complement intersects B complement, meaning everything excluding A intersects everything excluding B. So let's explain it with this illustration we have here. So the illustration we have here, we have 2, 3, and 1, 2, 3, 4 for A union B. So if we say A union B complement, A complement means remove A, B complement means intersect, B complement also means remove B completely. Now, their intersection of A complement and B complements, anything that contains A and B, remove it, terminate it as well. So if we have A union B complement, it means our final answer will just be 5. That's C. As long as it's not part of, okay, anything that is not part of it, get it out of the equation. So now, De Morgans explained it like this. If you have A union B, flip the sign in the union to the intersection, and then you place the complements on A and B. So if I have A intersect B complements now, A intersect B, all complements. First thing I do for De Morgan's law is what? I flip the intersection sign to union first. Then this is A complement and B complement. And boom. We can now, if you just stare at the Morgan's law, or they're asking you which of these, because in our test, they ask us which of these is a De Morgan's law and all that. You just know, did they flip the sign? Yes, they flipped the sign. All right, that's De Morgan's. They flip the sign and they put the complement on both of them. Okay, that's De Morgan's. That's what you should just check for. Your eye should just go straight. Was the sign flipped? It was flipped. Did they spread out the complement? Yes. Okay, that's De Morgan's law. That like should be your target. So, and then we have the last one, which is the identity laws. Yep, we have the last one, which is identity laws. Identity laws. Okay, so now, for identity laws, it's just telling us that when, what is common? Okay, let's see, someone, okay. I thought someone raised their hand. Okay, now for identity laws, do you have any question? Are we clear on De Morgans? Okay, we're good. All right. So let's just treat the identity laws. It looks like the set is, we've not gotten into Venn diagrams yet. And we have 2 subset problems. We have 3 subset problems. Do you think you want to take a break first and then come back, or we should continue? Okay, we should continue. All right. Now, okay. All right. Okay. So we can, the meeting will be open, so we can take a break. All you need to do is you just come back. You can come back in 30 minutes. 1 second. Let me just set that. Let me see. One second. So just to, yes, you have a question, Ezra, and yeah, Ezra, great, and all yours. Yeah.
Good morning, sir.
Yes.
So please,
Good morning.
wanted to say, could you please do a quick recap before the break? I mean, some of us came in late. You could just run over it quickly before the break, please. Thank you.
All right. Okay, I'll do that. And what about you, Praise? You have your hands raised.
Finish it today.
Praise?
Can you hear me?
Yeah, I can hear you.
I said the topics that we're supposed to cover, are we going to be able to finish it today?
As long as you're available, yes. We'll finish
Okay.
it.
Really, really. Problem.
Okay.
Thank you.
All right. Okay, so let's have a recap. Let me finish the identity. Since we're going to have a recap, why don't I just finish the identity laws first? Okay, so um, identity laws is telling us that we have A union. The A to the union of an empty set is equal to A. And likewise, the A to the intersect of a universal set is equal to A. So what this is telling us that when A to the union of an empty set. So let me just explain this. Let's explain this thoroughly. So A to the union of an empty set. When we say empty set, and let's say we have a universal set here, everything is contained in a box, meaning that that's going to be our universal set. So let's say we have the universal set. Now, A to the union of a universals of an empty set is what is not inside this set is the empty set. All right. So what is inside this set is 1, 2, 3, 4, and 5. Right. So A to the union of just the empty set means we're focusing just on A. A union nothing. So A union nothing is just A. And what do we have in A? We have 2, we have 3, and we have 4. That's in A. Just A alone. All right. And identity law is telling us that A to the intersect of the universal law, that is the box, is still A. Because we're trying to say what is in A that is common in the universal set. Whatever in A that is common in everything is still falling under A. That same A. So whatever is in A that is common in the entire set is still A, right? So that's just A. Identity laws goes further to explain that A to the union of the universal set is equal to the universal set. Trickier. And then A to the intersect of an empty set is equal to the empty set. Now, what does this mean? A to the union of a universal set means A and everything in the universal set. So A union, remember I said union is like comprising everything together. So A union the entire set, which is the entire set. That's why we say A to the union of the universal set is the universal set. So everything in A union the entire set is still the universal set. Now, the second one is saying A intersects an empty set. So what that means is what is in A that is in the empty set? Actually, there's nothing in A that is in the empty set. Empty set is just empty, it's just there. So that means that's also an empty set. But one of the things that tricked us the most in the test was the De Morgan's law and distributive law. Okay. I had complaints that we made mistakes in that part. And I was like, whoosh, that got us. But this is just the breakdown. So let's go back to where we started. So we talked about, the first thing we talked about was sets. We said set is a collection of objects. It could be numbers, things, places. And then we talked about the universal set, which comprises of everything in the set. Looking at this A, B, the universal set here is 1, 3, 5, 6, 7, 8, and 9. Everything in the set. That's the universal set. Then we talked about the set of A and the set of B. Let's say the set of A has 1, 3, 6. Set of B has 3, 6, 5, 7. And then we say the union of A and B is going to be everything in A and everything in B, which is 1, 3, 6, 5, and 7, since they are all common. Then we also talked about the intersect. That is what is common between A and B, and that's just 3 and 6. Then went further to talk about the universal set, says all Miva students in Lagos State. And then I said if A is for software engineering department, if B is for cybersecurity, and C for public health. Okay. and that is the universal set. The subset A is a subset of the universal set. Subset means sets that can be found in the universal set. B is also a subset, and C is also a subset because we have students in this department. Then we went further to talk about the power set. We said that when having a power set, or how to find the subset of a set, is you put it in power set. Power set has a formula of 2 to the power of the number of elements inside that set. So 2 to the power of how many elements are here in A? There are 3 elements, 1, 2, 3. So we raise 2 to the power of 3 and we get 8 subsets. Yes, everything in the box is the universal set. Everything, including the ones that are outside, is also all part of the universal set. All of them. Okay. Then we started deducing the subsets. We said the empty set, we have the empty set. Empty sets are always subset, just like when you're trying to get your factors, and 1 is a factor of every number. The same thing with sets. Empty set is a factor of everything. So we have an empty set, we have the sets, we have 5 alone, 7, 8, then 5, 7, 5, 8, 7, 8. These are the ways we can derive subset. These are different ways different sets can come out from just A. And how do we know there are 8? We use power sets to calculate that, to know that there are 8 subsets. Then we went further to talk about equal sets. We said equal set actually has to deal with the elements inside the set. For instance, X equals A, B, C, D, and Y equals B, D, A, C, D. As long as the elements are the same, they're counted as 1. So the elements inside, that's what equal set talks about. So X is equal to Y, and then X is equal to Z because they're the same. Okay, but X is not equal to K because K has F. So something is different there. Then we went over to talk about equivalent set. Equivalent set uses the hamburger sign, and we have 1, 2, 3, 4. Equivalent set actually has to do with the number of sets, not the element, the number of sets inside that particular set. So there are 4 elements here, and there are also 4 elements in B. So that means A is equivalent to B. And A is, but A is not equal to B because of the subsets, you understand? The subsets are not there. So A is not equal to B. Okay. Why is A not equal to B? Because B has a different element, A, C, D, E. They can be equivalent because the number of elements in B is also 4, and the number of elements in A is 4. So they are equivalent, but they are not equal. But we can say B is equal to C because they have the same elements. If you match it together, you see that they have the same elements. So, yes, they are the same. So, what else? It's not here. So let's talk about, then we moved over to talk about, yes, the element of, other denotions. We have elements of, we said, if Y is equal to X, such that X have numbers between, set X is the numbers between 10 to 15. Then we say this sign means element of 11 is an element of Y, and 12 is an element of Y, and 13 is an element of Y. But 30 is not an element of Y because it's not comprised in the definition of the set given to us. Then we also talked about the cardinality of sets. We said X equals, we have A, B, C, D, which means there are 4 elements. So cardinality is represented by a small letter n and then the set X in parentheses, which is 4. And if you count that of Y, 1, 2, 3, 4, 5, 6, you have 6 as the cardinality. And then we went further into complement of set. When explaining complement of set, you just understand that complement means what that set has, excluding what the set has. So to find complement of set, you need to find the difference in set. And to find the difference, you eliminate. So how do we find the complement? We said the union set has 10, 20, 30, 40, 50. And Y has just 20 and 50. To find Y complement, you use the union set minus Y. So we stated everything in the union set minus everything in the Y set. And all we did was, we don't subtract per se, we just eliminate what is the same, what is common in both of them. And we're left with 10, 30, and 40. So the things that are there Okay, that is the complement. And you can actually express complements like this is denoted by either using a prime sign or using a C prime, C sign. So whichever way they write it for you, so you don't get confused. Then we went over to talk about the disjoint set. We said that when we don't have anything common in any set, like X intersects Y, there is nothing common here. That's an empty set. This set is called disjoint. While a non-disjoint set will have at least one element that is common, that is non-disjoint. Then we have the laws of sets, which we talked about, the idempotent law. And for idempotent law, we say anything that belongs to A is A. So everything for A stays as A. A union A is A and A intersect A is A, meaning that A is minding his own business. That's independent law. So if you see something like this in the test or in the exam, you just know, oh, A union A is A, or X union X is X, and X intersect X is still X. That's idempotent. Just pick your idempotent option and be free. Then we have associative law. Associative law is saying, first of all, we just comprise it together. A union B union C. It is A union B, and the same thing with union C, because they are almost talking about the same thing when you are associating the properties. So we use this for example. A union B union C is 1, 3, 4, and 5. Everything in B and everything in C. Then A union B union C will be 1, 2, 3, 4, and 5. I just explained this. Now, to see that it is associative, we try it. A union B is 1, 2, 3, 4. And then when we put union C, it is still 1, 2, 3, 4, and 5. So you see? So that is what we call associative property. Likewise, the same with intersection. A intersects, okay, let me explain this part. B intersects C. What is common in B and what is common in C? So what is common in B and what is common in C is just 4. Right? And then A intersects B is just what? 3. So for A intersect B intersects C, we have 3 and 4. Now if we come here, A intersect B is what? 3 and what? 3 and 4. And then intersect C is still the same thing as 3 and 4, because this is just what's common in AB and also intersection of C. This. So this is how associative law works. Then we talked about commutative. Commutative is like saying 2 times 3 and 3 times 2. A union B is the same thing as B union A, and because 2 times 3 is the same thing as 3 times 2. A intersect B is the same thing as B intersect A. So that is commutative law. We're saying that they're the same thing. So if I say 5 times 2 is 10, 2 times 5 is still 10. So that is commutative. Then distributive is just like you opening a bracket. When you want to open bracket, in US they call it distribution. Here we call it opening of bracket or expand or open that bracket, how our teachers used to call it. So it's just like you multiplying everything inside. So this would be 3 times X plus, you put a sign there, 3 times Y. Same thing with distribution, distributive law. A, it will be A intersect B, union, A intersect C. You see that? And then for this one, it will be A union B, intersect A union C. Just like you're opening the bracket here, 3 times X plus 3 times Y. This is what we call distributive law. And then for the De Morgan's law, he's saying that if we have A union B complement, it means A complement intersect B complement. The sign flips. If the sign should flip and you distribute the power, that's the complement on each of the sets, you have De Morgan's law. That's how you determine De Morgan's law. Just look for, when they are saying which of these is De Morgan's law, check, did the sign flip? The first thing, yes, it did. Does it have the prime on both sets? It does. Pick your answer. That's De Morgan's law. So if we have A union B, first thing you know that the sign flipped to intersect. Here we have A intersect B. First thing you know that the sign flipped to union. You already know your answer already. You know where you're going. That is the Morgans. Then we have identity laws, and that is the last I just explained before the class. So before we go on our break, the break is going to be for 30 minutes. If you want to go on the break, you can go. And for those that will not be going on the break, I just have a brief presentation about, let me see. Yeah, a brief presentation about what I do. So please help me 1 second. So I'm going to start the timer now for the break. And so we have 30 minutes. Well, for those that want to see what I do, just know more about me, please, you can just wait behind. It's just going to take 5 minutes and I'll be done. Okay, so what I do. Actually, my name is Gideon Wakama and I run a STEM club. Okay, so the STEM club, we all know it as science, technology. Sorry about that music. We all know it as science, technology, engineering, mathematics club. So first of all, we have an agenda, and the agenda, I like music, don't blame me. The agenda is agriculture, technology, and power. We have strategic placement to enhance educational tech programs. We want to recreate those programs. Actually, it's mainly me and my team. We want to distribute skills to boost productivity for the country, engage in power, productivity, engineering, and ensure education gotten is used for national development. Emphasis on national development. So me, the team, that is me. I'm actually also a Miva student too. I'm not your lecturer. So my name is Gideon Wakama. I'm actually the lead and chief operating officer for mathematics and STEM advocate. I have a 9 years experience of teaching, and I specialize in guiding secondary school students, candidates, and university students in mathematics, physics, chemistry, while fostering critical thinking and innovation. I'm the founder of Educational Asset Development Initiative, Learn Academy, Rebound Foundation, and the STEM Club of Nigeria in collaboration with Innovation Center Africa. So I also have my lead engineer here as Mazi Michael Iyekwereme, very funny name, huh? And his experience in mechanical engineering as well, with over 6 years experience in the field. He's also an educating enthusiast. I have here my secretary, virtual administrator, Victoria. She has 3 years experience. She helps us in coordination. And then we also have someone that does gifts. She's an assessment review officer and media coordinator. So it didn't just start now, all right? The STEM club was formerly Mathematics Club, which started in the year 2019. What I do is I go into communities and I seek for potentials by building a platform where they can be better and develop themselves. The target is the future, and that is the children and teenagers. So we need to catch them young before they become solid rock on the mentality. So in the year 2019, 2020 academic session, that was my first scholarship that was issued out in Math Club after I hosted a regional mathematics competition in 2019. It was the first of its kind and the area was lacking of social impact, so I initiated a potential development initiative and invited schools to participate in what is now known as the zonal competitions. It wasn't easy seeking for sponsors, as most of them were not after impact of children or next generation. They don't even care what I say. So I raised funds myself using my skills and taught the philosophy of, if I as a Nigerian can do this for you and sacrifice for you, then you can do it for others. You can sacrifice for the nation as well. So the mentality is what I seek to drive in this movement. Now, I didn't only go into mathematics. I had mathematics and debate. I also taught sports and athletics for children and teenagers who are gifted in that aspect, creating competitions and communities that will grow together. As well as taking my boys out for other competitions, they got exposed and noticed. Just in the span of 2 years, we grew from 7 players to 40 plus players, all free in the academy, because money in communities are like a barrier. And when we don't invest in these initiatives and infuse money, we can't reach people or see the real talent. So we as youths can create something for ourselves through this initiative. Well, as of 2021, 2022, we won multiple awards in the Football Academy, right? Touching and impacting lives in every direction and applying the same philosophy. There are some of us that were recognized by Habit brand, okay, and we were given special awards there. So fast forward to 2024, where I transformed the Mathematics and Debate Club into just one. Okay, where I transformed the mathematics. So I did that 2024, just 2 years ago. I transformed it into just one demanding unit, which is called the STEM Club. So I fostered into getting in communities and developing the next generation on agriculture, tech, and engineering in power generation. So in this part here, we made our first our first power bank. And then in 2025, which was just last year, we progressed into a solar power bank, which we just concluded. So just last month, we were invited by the Federal Technical College to showcase our works from the STEM Club Lagos to see how teenagers are instilled with tech education and engineering on renewable sources of energy via engineering. The agenda is to continue to ensure we can reach at least 5,000 youths by the next quarter of the year. And we create a platform where they have access to advanced tech courses. So I also want to create more competitions to promote unity in the knowledge of agriculture, tech, and engineering. Right now, we're still dealing in agriculture. We've done engineering, and we've progressed into tech. So I believe that the youths can do anything if they really set their minds to it. So the social impact is create and promote communities and competitions that can bring a combined front in agriculture, tech, and engineering. So the strategy, okay, is the youths. The strategy is to train some teenagers in platforms like Code Academy and Data Camp, and they can in turn transform these courses into modules for our Nigerian citizens to gain access to free of charge, and they can get certified by my collaborative organizations like the Innovation Center Africa, which is also an organization in tech. I believe the youths can do anything if they really set their mind to it. Ever since the NSAS, we have proof that unity can conquer, and to make a change, we need to build and not venture into passive aggressions like protest. We need to build to make the change, and we start by building our communities. So this has been 9 years of my life, and I've been in the educational sector, and most times I use my funds or I try to raise funds. So my fundraiser target, right? The fundraiser target is $3,000 to train some youths and teenagers and to transform these trainees into courses. So if you feel this is something you want to be a part of, you have ideas that you can bring to the United Front, you can reach out to me at g.wakama2314@miva.edu.ng or gideon.wak@gmail.com. And that is my number, my personal WhatsApp active number. So thank you very much. If this is something, please just reach out to me through those further details. And thank you for listening. I truly, truly appreciate. Okay. So that didn't take 10 minutes, right? So for those that stayed, I really appreciate. Thank you. Yes, Ojima, Princess.
Okay, thank you so much, Gideon. I love what you do, and thank you for hosting the class. You actually helps a lot of us. So I wanted to ask if you host virtual classes for kids.
Yes, if we host virtual classes.
Yeah, that's what I want to know. Do you host virtual classes for kids?
Oh, yes, I do. I started the Learn Academy 2 years ago as well. So I host virtual classes for kids. I train kids in coding and also in mathematics, per se.
Is it only mathematics or both other science subjects?
Yeah, science subjects as well. chemistry, physics, other maths, as long as it is science related. I do that.
Okay, and I hope you're affordable.
Oh yes, yes, sure. I
Okay, I'm going to reach out
am.
to you later. So we'll
All
talk.
right. Okay. Thank you. Yes, Osioma, I can see Genevieve, I can see your hand.
Yeah, Gideon, thank you for the class. I appreciate and I also love what you do. I hope when I have money, I'm going to like contribute to your program. So what I want to ask is this holiday that we're going to have, I don't know if you're going to be chanced. Like I need you to like help me or fill me in with some physics and mathematics education.
Of course. Has Miva told us the holidays that were they've not issued that yet?
After the exam, we are going to have a holiday. Are we not supposed to rest? Yeah, we are supposed to rest.
Okay, it's automatic. Yeah, we'll schedule something. We'll see how we can deal with that.
Okay, I hope it's going to be affordable.
Yeah, when you guys say affordable, what do you mean actually?
Affordable. What till we go fee pay for now? Like what we can pay for, not what is beyond our,
Yeah,
budget.
yeah. We'll talk about that.
Okay. Okay, I will DM you on WhatsApp to talk about that.
All right, no problem.
Thank you.
You're welcome. Yes, all yours. Okay.
Okay, good afternoon, Mr. Gideon.
Yeah, good afternoon.
I want to give you accolades for what you do. So I was asking a question earlier. If you outsource children from just school or externally, those not in school.
I outsource them. Mainly, my target is going to schools because that's where the communities are. But if there are students or children that are also interested that I can get from outside, why not? My own is I find the funds for them, give them the access to the platform, train them, you know, giving them access to things that they might not really have opportunity to get access to. That's my main aim.
Okay, the reason why I asked is because I work for a foundation that we also do something like this, and we don't just reach out to students in school. We reach out to students outside school that we assist in education. So I'm thinking maybe if I talk to my boss about it, maybe we can also partner together. Would that be possible?
Yeah, yeah, sure. Why not? That'll be
Okay, I'll
possible.
reach out to you. Thank you very much.
Thank you. Someone was asking about my WhatsApp number. Let me 1 second. So this is the WhatsApp. So that's my contact details. If you don't want to reach me via Miva, you can reach me via personal email. I'm active. Okay. All right. So we have um less than 17 minutes for our break. Please, if you want to go and pee or you want to eat, or because most times I do have class marathons like this, and yeah, I'm used to it already. So if you want to go and pee or you want to eat or something, please stand up and stretch your legs a little bit so the blood can flow. We have less than 5 minutes to go. So let's start getting ready. So we continue and we cue sets. Right, so let's resume. So, yeah, so welcome back. Welcome back, welcome back. So I hope everyone is here. If you're here, you can just give a thumbs up. So I know that All right. Okay. I'm in class. All right. So let's now we know all the laws. Let's dive into the real main set problems. Okay. There are still a few things we talk about before we get into the real main set problems. And those things are just three. I want to ensure we touch every part. The first one we're going to look at is what we call the finite set. So it's what we call the finite set. They also ask this in the test, and then we have what we call the infinite set. So we have the finite set and we have the infinite set. Now, for finite sets, just think about finite set as things that have, think about finite set as things that are countable, things that you can count. Okay, that's what finite set is. So for instance, if we have a set, let's say we have the set U. I can't use U. U is like universal. Let's say we have a set T. And the set T is telling us that we have all lecturers in Miva University. So that is a finite set because we can count it. So this is telling us all lecturers in Miva University. In Miva. So telling us that is a finite set because it's something that we can count, right? Or sometimes you say all students who registered for what WIAC examinations or for JAMB, it's a finite set because we have a data. We have something that we can represent. But for infinite set, there are things we can't count. For instance, things that are infinity, uncountable. Let's say we have a set. Let's say we have a set D. And in the set D, it is defined by X, such that X means, or X is belonging to all natural numbers. So when I say all natural numbers, I mean all natural counting numbers, like 1, 2, 3, 4, 5. We keep on counting till infinity. That is infinite set. We keep counting till infinity. So it's something that we cannot just conclude. Okay? Or we say, let's say we have a set of Y, and Y is, the set of Y is X, such that X, what X means is X belongs to probably set of all integers. So let's be C. The set of all integers, C. This is representing integers. So we know what this is. So set of all integers, and let this just be D. So integers will range from both the negative numbers down to the positive numbers, and we keep going till the infinity. It keeps going like that. That's infinite. So that's just the difference between finite set and infinite set. One we can count, the other is uncountable. Then we have what we call the range set. Now, as for range set, we have the, now as for range set, in here, we call range, or we define range by a given set. So range actually deals with strict inequalities, and I'm going to explain that part. It actually deals with strict inequalities. So for instance, inequalities, when I say inequalities, I mean the less than sign, I mean the greater than sign, I mean the less than and equal to sign, I mean the greater than and equal to sign. This is what we call inequalities. All right, so any set defined by strict inequalities, what that, it does not accept numbers at the boundaries or limits. Okay, so we have strict inequalities and we have weak inequalities. So this is a strict inequality. The greater than and the less than, strict, and the green represent weak inequality. Or wait, let me just put that in another way. Let's green represent the strict inequalities and red represents the weak inequalities. So what this means is, I'm going to explain. So for greater than and less than, what it means is if I say all numbers greater than, x is ranging from all numbers greater than 2, it means it's an infinite set. All numbers greater than 2 keeps going on and on, 3, 4, 5, 6, 7, 8, till forever. But you see this one that has limits, that's the weak inequalities, the one that has equal to. We can say x is ranging from all numbers. We can say x is ranging from all numbers greater than or equal to 10. So we know that, okay, there's a definition that it has to be greater than or equal to 10 first before we start counting. Okay, or we say less than or equal to 10. So that means if x is less than or equal to 10, so all numbers that are less than 10 till it gets to 10. That's the meaning of less than or equal to 10. All numbers less than 10 and equal to 10. So if we're stating all numbers less than 10, we can say minus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We stop at 10 because this is giving us a defined boundary. All right. So now when you're dealing with range set, I'm going to write out some examples here. So we can, because we had a lot of range set examples that was given to us. So let's say we have the set of G, and G is X. G is a set of X such that X means 1 less than X less than 5. I'm going to break this down. Don't worry. You will understand the true meaning. So 1 is less than X, which is less than 5. So for you to understand clearly inequalities or range set like this, you need to first of all understand the concept of a number line. Now, remember your graph. On a number line, you always have 0. One side is negative, -2, -3. If we remember how we did graphs that year, then another side is positive. We have 1, we have 2, we have 3, and it keeps going on and on like that. So if we say 1 is less than X, all right, and X is less than 5, what this is saying is that it's giving us a definition of where we're going to put our range from. It's giving us a definition of where we're going to put our range from. So let me say 5 is here. So there is a definition of where the range starts and where the range stops. So this is X. 1 is less than X and X is less than 5. So the range for the set of numbers, this here is a strict inequality. So for strict inequalities like this, or for open statements like this, we do not include the 1 because they just said less than 1, but they didn't say less than or equal to 1 there. So G, according to this, will just be the element 2, 3, 4. That's the meaning of that set, range set. That's G. So do you have any question in this? Any question? Okay, so we're good. All right, we're good then. So, oh, yes, Mr. Rabbi, you're here. What's your question? Yes, Is it rabbi or king? Okay, Mark says, why is the 5 not indicated? No, it's not always represented with line. I was using the number line to explain what it means, but most times they won't teach that. They will just go straight and tell you what it is. So they won't tell you it belongs to a number line, but that's how you understand inequalities. Now, it is not including 5 and it's not including 1 because it is not, it does not have boundaries. It's not a closed statement like this. This one says less than or equal to. Less than or equal to means that this is going to be shaded and we're going to include 1. Then if it's greater than or equal to, this will also be shaded. It's going to be a closed statement. And then we're going to include 5. Do you understand? So because it is not included in that aspect, they didn't put less than or equal to or greater than or equal to. That means we're not going to include 1. It's just less than that is here. Okay. All right. Yes. Okay. So let's say we have, now let's take another one, range set. Let's say L such that Y is equal to, Y is 16 less than, L is given to be a set such that Y means 16 is less than Y, which is less than or equal to 19. So if we want to understand this clearly, the reason I do it on a number line is so I can explain what this means. So if we want to understand this clearly, just take your number line. You can do this in your head, you can put a number line in your head or somewhere at the back of your mind. I just want you to have clear understanding of what it means. So we have 5. Let's start our number line from 15, 16, 17, 18, 19, and it keeps going on like that. 19, 20, and like that. So this one says less than. We have a definition. That's an open statement because it's not less than or equal to. And then it goes down to what? Less than or equal to 19. So that means this is here is closed. So this is where Y is. So what we're going to have here, we're not going to include 16 now. We're just going to include what? That's going to be 17, 18. Because this has less than or equal to, we include 19. That's a defined set. See that? We include 19. And that's what it means. Do we understand that? All right. Great. Okay, so now we understand range. Okay, Praise says no. Okay, what's your question, Praise? You have a question? Okay. All right. So, okay, I'll go over it. Let me use this part. We said G is such that G is a set of X such that 1 is less than X, which is less than 5. And this one we call open statement, meaning that, yes, the whole class is being recorded. The board is also being recorded. The meeting, everything is being recorded. So the board stays. I can screenshot the board and also send. So this means that 1 is not included and 5 is not included. So everything, you're welcome, everything that is less than 1 is less than X. So we take the numbers that is less than X here, and then we put it on a number line down to 5. This is the range set of values, 1 to 5, right? But they did not put equal to, less than or equal to in that part. So instead, we're going to leave it open, meaning that we're not going to include 1 in our numbers. We're not going to include 5 in our set of numbers. So we'll just take 2, 3, and 4 because this is not equal to sign. Now, if you look at the second example, praise, you see that this one says L is a set of Y such that 16 is less than Y, less than or equal to 19. So we put our range of values from 16 to 19, right? And then we're not going to include 16 because it does not have the equal to sign. It just have less than. But 19 has equal, less than or equal to, so we're including 19. So we take the range of numbers in between that part, 17, 18, and then because of this inclusion, we put 19 as well. And that is going to give us the range of value of this. This set means this. That's the meaning. We're going to do another one. Let's say we have M. Okay, let M be equal to, let's say we have a set of A such that 25, 1 second, such that 25 or is okay, 25 is less than or equal to, you see now that's a less than or equal to sign, so that means we're going to include 25, and less than 30, this is just less than 30, meaning we're not going to include 30. We're not going to include 30. Can we see the screen? Okay, so if you can't see the screen, it probably is network. You can log out, log in back. I'll just pause here for 5 seconds or 10 seconds. Okay, you can see it now. All right, so it's network, right? Okay. So now, in order for us to deal with this, now we can just put this, remember, put this at the back of our mind. What this means is if we have a set of numbers, let me say 23, 24, the range is starting from 25. The range is going to start from 25 according to the definition of the set. And then we have 30. So now 25, that's where the range is starting. This is a closed statement. So this is shaded, meaning that we're going to include it. And then down to where we have 30. 30 is just open. There's no less than or equal to sign. So this is A in that range. So my set of values here is going to be what? Set of values will be, can anyone help us? That's going to be, you can type it. Okay. So set of values here, meaning that's thank you. So thank you, Mark. So that's going to be 25, 26. We're going to include 25 because there's a less than or equal to sign here. 27. Thank you, John. Thank you, all yours. 28 and 29. But we're not going to include 30. We'll stop at 29 because 30 does not have an equal to sign. You see that? Doesn't have the equal to sign. So the range there is just 25 down to 29. Yes, that's what it means. Okay, do you understand that? All right, let's take this last one and understand range once and for all. So let's say we have N. N is a set of B such that B 3 is less than or equal to B and less than or equal to 6. So let's do that. Let's see. Less than or equal to 6. Correct. 3, 4, 5, 6. Yes. Yes. Yes, Michael. 3, 4, 5, 6. That's correct because 3 is inclusive and 6 is also inclusive. So I think we get the gist of range of sets. So whenever we do see this, this kind of questions are always asked. You see this in our, how do we call it? You see it in the Miva questions and all. You see set of this, set of that, and you're able to actually answer it. So we're dealing with sets, and now, so since we understand that, we now know the range of values, and we know number sets. So let's move on. And let's move on into I've touched the main things that are here. I want us to move into Venn diagrams now. So now that we have clear understanding of range sets, we have clear understanding of finite and infinite sets. So I just have a question. If I have a set like this, if I say, given that, let me just put a question here. Given that W is a set of X such that X is even number from 5 to 15. Can you tell me the elements? Such that, let me put it here. X is even numbers from 5 to 15. So even numbers from 5 to 15. All right, so can you tell me what's going to be 6, 8, 10, remember to 15, to 15. So yeah, 6, 8, 10, 12, and 12, 14. Yes, 6, 8, 10, 12, 14. That's correct. So we have clear understanding of that. Let's move to Venn diagram, the main boss in this whole set thing. The yoga pata pata of the whole thing. So for Venn diagram, it's just like what we've been dealing with here. So do we have any question on this before we move on to Venn diagram? We've already even started Venn diagram with this, but we'll go deeper into it. And that's like the last part here. But there are lots of things we need to understand though, which I'll break down. We have multiple examples, don't worry. We'll touch it. So, do you have any questions on this? Okay, we're good. All right, let's move to Venn diagram. Okay, let's go into, Venn diagram by John Venn. So instead of having representation of, having to deal with numbers just mixed all around like that, John Venn, a mathematician, was like, why don't we just put it in different ways or represent these things pictorially using boxes and circles? And that's how it came about, the Venn diagram. So they named it after him. So due to everything that we've learned so far, we've actually started the Venn diagram in this aspect here. So I feel I'm going to just throw a brain teaser and let's see how we deal with the brain teaser. So let me ask this question. See, it is this. So, okay. The set of A is read such that we have 1, 3, 5, 7, 9, 11. Okay, let's do that. And B is equal to, this is a brain teaser, so you first try it for just 60 seconds before we attempt it together. And 15. And C is equal to, let's say, 3, 6, 9, 12, 15. They are subsets of our universal set. and let that be 1, 2, 3, down to 15. That's the range. First question. Draw a Venn diagram. Okay. To illustrate this. Second question. Let's use our Venn diagram we get to find. So I'll be putting that here. We're going to use this to find, C intersect A, C intersect A complement, and we also use it to find this A complement. So who can tell me if this is distributive or associative? A complement intersect B union C. So, but first, before we start solving, what property is this? This one here. We can check, can go back and check our properties. So, what property do you think that second distribution? Very good. Okay, distribution. Yeah, that is a distributive property. So if you look at it closely, it's just like you're distributing. All right, so let's solve. So the set of A equals that, and B equals that, and C equals that. And they're all subsets of the universal set. So how do I do it? Do I put it as 60 seconds or how? Okay, so can we do it in 60 seconds? Just an illustration. Try and attempt it for 60 seconds, and then we'll see from there. Just 60. Using the same knowledge that we've used previously when we were dealing with A, B, and C, that kind of thing. So let's see how we can distribute the property. Don't worry, I'll break it down, and we'll see the illustration and analysis of everything. Welcome to Venn diagrams now. Oh, the board. Sorry about this. 1 second. So this is your board. You say time don't finish. Ah, God. Try it again. You have another 60 seconds. Yes, time round. All right, let's do it now. All right, 60 seconds and counting. Let's use that one. $35 seconds. Okay, 20 seconds. 6, 12, and 15. That is correct, John. We have 5 seconds. Okay, time's up. All right, so let's do it together. Yeah, 6, 12, and 15. Yeah, that is correct. Mark, I think you wanted to write 12, right? That should be a typo, right? Okay, so let's do it together. Yes, you got the first one right. To be able to draw the Venn diagram, we must list the elements of the various intersection. Okay, so we have set A, set B, and set C. Do we have anything that is common in all of them? Set A, set B, and set C. So if I'm going to list this, I'll just put this here. Let's say A intersect. That's what's common in both of them. B intersect C. Yep. Thank you. 3. So we have 3. Okay. Now, do we have things that are just common in A and B alone? We're trying to know how we're going to put out the diagram. So things that are just common in A and B alone. So things common in A and B, but C is excluded. Things common in A and B, but C is excluded. Remember, C must not be part of it. Okay, 5, 11, yes. C is excluded. That's C complement. 5, 7, 11, yes. So we have 5. Let me explain that. 7 and 11. So when I put this, just A intersect B, excluding C, meaning anything that concerns C, we're not going to include it. Anything that concerns C, we're not going to include it. Okay. This concerns C, that's C complement or C prime. Anything that concerns C, we're not going to include it. So now we're not going to include it. So what is just left for us is common in A and B is 5, 7, and 11. Yeah. Okay. Yep. Okay. Now that we know that. All right. So let's list another thing. What is common in just A and C, excluding B? So that would be B complement. Then just common in A and C, excluding B. We list that one out too. So we can know how we draw this Venn diagram. So, or you can know how to interpret the Venn diagram. What is common in A and C alone? But remove 9, correct. So we have 9. Good, so 9 stays there. And what is common in just B and C? So that's A complement and B and C. Just B and C alone, excluding A. 15, correct. Thank you. 15. All right, so if you don't understand how we did this prime and complement, you can ask your question before we draw that Venn diagram now. All right, Amina. So here for the first one, we said that this has a C complement, right? We're looking for what is common in A and B, but excluding C. So whatever C has, we're going to exclude it. There is 9 in A, 9 here. There is 15 here, 15 is here. Just remove it first. We're looking for only what is common in A and B. So there's 5, that's 5, 7, and 11. There's 5, 7, 11 in A and B. So that is C complement. Now, if we're looking for B complement, okay, let's say we're looking for B complement. Okay, question 2, 2, 6, 12, and 15. That is correct, Okon. So if we're looking for B complement, so what is common in all of them here? What is common in all of them? Yeah, excluding B. So anything that has B, we remove it. So we said only 9 because 3 is common in B. So remove it first. 5 is also common. So remove it as well. 7 is 7 is here. Also 7 is also here. We're excluding B. So anything that has B, we remove. Oh, Eno. Eno. Sorry. I saw Okon, that's why. Sorry. So what's common in just A and C? So do we have 11? 11 is here, remove it. And what else? 15 is here, remove it. So just the one that is common in A and C, excluding B. Anything that concerns B, remove it. So that's just 9. That's why we have 9 here. I mean, then A complement, the same thing we're going to apply for A complement. So whatever there is A complement has, we're going to remove it, and we're going to be left with 15. That's how we get it. All right. So let us draw that Venn diagram. Let us interpret this correctly. So I'm going to, okay, first of all, let me just put in my circles first. Hold on. Let me put my circles. So the first thing is going to be, let me put my A, and then let me put my B, and then I should have another C. Okay, so let me put this here. So I'm going to move this here. Okay, good. So now I have this as A, I have this as B, and I have this as C. A, B, C. So from all what we've explained, the one that is just common between A and B, we said it is 5, 7, and 11. So we have 5, 7, and 11. The one that is just common in A, B, and C, we said it's just 3. So we put 3 here at the middle. This is what it means. The one that is common in A and C alone, just A and C alone, this is what we got. B complement, so it's 9. The one that is common in B and C alone is 15. So what is left out from the ones that are common in A? 1 is left out. What is left out from the ones that are common in A, B, and C? For B, 2. And what is left out from the one common in A and B and C? For C is just 6 and 12. Then we have our other elements as well. We have our other elements as well. We have 4. We're going to write all those ones out. We have 4, we have 8. We just put it in the box. We have 4, 8, 10. We have 13. And we have 14. Okay. So those are the other elements that are in the universal set that are not contained in A, in B, and in C. We just list them out here because they are all part of our universal set. These are our universal set U. So they are all part of the universal set. So now the first question says we should find C intersect A complement. C intersect A complement, meaning that everything that is belonging to C, all right, but A should not be involved. Okay, first question, this is the first question. C intersect A complement. So anything that involves A, take it out. So if we check here, this is what I'm going to take out. I'll take everything that concerns A out of it. As long as it's touching A, you move out. I don't need you in that place. That is A complement, okay? And what I'm left with is just, we got the answer. That is 6, 12, and 15. That's how we read it. And everything that is, the next question was A complement, all right, intersects B union C. A complement intersects B union C. So anything that is just B union C alone. All right. So B union C alone. So we're going to have, but it must exclude A. So 6, 12, 2, and 15. A complement. That means A is not going to be part of it. Intersect B union C. So everything of B must exclude A. That's A complement. So we have the 6, 12, 15, and 6, 12, 15, 2. Or 2, 6, 15, 2, 6, 12, 15. Anyone you like. And that's how we read it. So this is just a clear understanding or a start of this is a start of Venn diagrams and what it entails, how you can represent the Venn diagram, how you can interpret the Venn diagram, and things like that. Do we have any question? Because now we'll be treating two subset problems. I'll be treating 3 subset problems, where I'm just going to give you a secret formula where you can maneuver any kind of Venn diagram that comes your way. So, okay, so we can go on. Is there an easy way to solve this? Yes, there's an easy way. That's what we're dealing with now. No time for exam. There's an easy way. When you look at it, I'm just going to tell you a formula when we're dealing with 2 subset problems and when we're dealing with 3 subset problems. That's what we're getting into. So we use the formula straight up, and yes, Israel, we don't need to do all this, long cut. I just needed you to understand first. Yes, Israel.
Yeah, sorry, I didn't meet the beginning of this Venn diagram, but I wanted you to try something. If we are to list the elements in A prime or A complement rather, what would that elements be before we do the C intersect A prime? Because I was thinking A prime or A complement is going to be involving all the other elements in the universal sets that are not in the set A. Okay.
Yeah, so that's why we shaded everything, because A complement, A itself is involving this. Okay, so for A, right, A belongs to this in the universal set. These ones now are not part of the set. They're just outside the set. Okay, so they're outside the set. If we're to list all the elements in A complement in that set that involves C and A, according to the question, so we exclude whatever thing that concerns A and only put what concerns C.
Oh, okay. So you're not considering the other elements that are not part of those 3 sets, which is 4, 8, 10, 13, and 14, from what I'm saying.
No, they're not part of A.
Oh,
they don't involve A. They are just in the universal set, They don't have a set, actually. They are just outside.
Yeah. So the reason I'm asking is that if this was to be maybe a different set notation, let's say maybe the set builder notation, and you list all these numbers, and you have a universal set, you want to list A complements. I was thinking to involve the other numbers in the universal set that are not in A. So
yeah, when
that's
it
why
comes
it's
to
quite confusing.
Okay. Yeah, we'll be dealing with that in 2 subset problems. Then I'll be able, this time around, we'll just deal with ordinary numbers and X, so it will be easier. This one is just a brain teaser for understanding. All right. Israel, right? Okay. We're going to touch that. You're welcome. Okay, let's move on. Let's progress. So we have let's move on to 2 subset problems. Let's deal with this. 2 subset problems. Okay. Now, this one is actually very interesting because it has to do with questions. You actually see questions, like they will set questions, and all you need to do is just solve. So, but first of all, let's learn a formula. I want to give you just a secret formula. For any 2 subsets, A and B, that are not disjoint, meaning they have an intersection, an active intersection. So for any two subsets, A and B, that are not disjoint, all right, the universal set, okay, when we say the universal set, we mean everything in the set. The universal set is the cardinality of A plus the cardinality of B minus the intersection of A and B. Don't worry, I will explain that in the example that I'm going to give now. So just take the formula to heart. Let's say we have two subsets as A. I had to say that, don't worry, fast, as A union B. Okay. And then we're trying to, for two subsets, right? So the formula is the cardinality of A, that means the number of elements in A, or the exact number of elements in A, plus the cardinality of B. Genevieve, this is the easy way to solve problems. We just use the formula, but I'm going to break down this formula so you can understand. A intersection B. Okay, just put it to heart. Let's take this first question. Let's deal with it. So just a quick question. In this lecture, all right, organized, let me say, for Miva student. All right, we are dealing with set theory, Venn diagram, and let's say types of sets. Okay. Okay, let's just say, let's deal with two first. Set theory and Venn diagram. Let's deal with that one first. So set theory and Venn diagram. Now, let's say in here, 25 people, 25 students are for set theory. And let's say 32 offer the Venn diagram. I'm just giving an instance. While let's say 13 offers both topics. Now, how many candidates enrolled for the lecture? Then another, yep, how many candidates enrolled for the lecture? So let's solve that. Altogether, how many candidates enrolled for the lecture? So let's see. So this is now involving two. We're going to say one is S for set theory and let V be for Venn diagram. So we'll just distribute it like that. One is S for set theory and let V be for Venn diagram. So this is set theory and this is Venn diagram. Now let's follow the formula. So the formula says we're trying to see how many candidates enrolled totally, right, for the lecture. Okay, so let's see for this lecture. So let's see. Let's use the formula. Set union, sorry, that's meant to be a union. Set union Venn diagram. This is going to be the cardinality of S. Instead of drawing Venn diagram and going through all those, you have two subsets, right? If you have two subsets, use the formula. The cardinality of S plus the cardinality of the Venn diagram minus the intersection between S and V, the Venn diagram. I'll also draw the diagram for you so you can get a clear understanding of it. So let's use the formula first to solve it straight up. So now we're trying to find the total students, how many candidates enrolled totally. So that means we're looking for S union V. That's for both sets, theory and Venn diagram. So now what's the cardinality of the set. According to the question, the cardinality of set there is 25. So we have 25, drop, this is 25, plus, now what's the cardinality for that of Venn diagram? How many offers Venn diagram? That is 32. So the cardinality of Venn diagram is 32. So we have 32. Then minus. Now, what is the cardinality of those that offered both sets and Venn diagram? That is 13. So minus 13. So to find the total, we just say what? 25 plus 32, that is 57 minus 13. That's 44 candidates or 44 students. Now, if you want to use, this is how the Venn diagram is going to look like. It's going to look something like this. Okay. And then we have 2 circles. One and another one. So okay, so one here is taken for S, the other one is taken for V. All right, so now S here, total of S, according to what we have, is 25. I'm just trying to interpret that. And for that of V, what we have is 32, right? Good. Now, the ones that are offering both is 13. That's set theory and Venn diagram is 13. Now, how do we calculate just S only? How do we calculate S only? That means those that is doing just set theory and not doing Venn diagram. All we do is we subtract from those that are also doing Venn diagram. We get 12. So for sets only, we get what? Just 12. Now for the same thing with Venn diagram only, what you do is we subtract those that are also doing sets from Venn diagram so that we can just get those doing Venn diagrams alone, and that is 19. So we have 19 here for Venn diagram only. So okay, well, how do we now calculate all the students that are doing the same, that enrolled for the course? So all you need to do is we add the ones that did sets only, the one that is doing Venn diagram only, and the one that is doing both of them, that enrolled for both of them. And we're still going to have 44 candidates or 44 students. So you can choose, whenever you're dealing with two subset problems, you can choose, should I use formula or should I draw the Venn diagram and solve it? And then you know. Any question? Okay. All right, let's try this other one. Let's say in a science class, 42 students, each student offers at least one of mathematics and physics. Okay. If 22 students offer physics and 28 students, you can see this is also two subsets. So offer mathematics, find how many students. Yeah, how many students offers both subjects. So we can as well choose the same thing. We can choose to do Yeah, we can choose to. This time around, we're looking for the one at the middle. We're looking for the intersection here. So we can as well just apply the formula. They've given us everything already. The ones that's in a class of 42 students. So that means we have our total. We have our universal here already. So if I'm writing down the formula here, I'm just going to say it's going to be the universal, which is physics and math, okay, is equal to 42. Is equal to the cardinality of P, all right, plus the cardinality of M, then minus the intersection of P intersect M. Now, that's what we're looking for, the intersection. So find how many students offers both subjects. So this is what we're looking for. So we just apply the formula. This is 42, right? Oh, 8 students. Thank you, Mark. Okay, 8, yeah. Thank you, Genevieve. So that is 8. So this is 42, right? So we just say that's 22 plus 28. This is 28 minus X. We don't know this. We don't know how many students offers both. We add it up together. So this is going to be, this is 50 minus X. Then we have 42. So this is 42 minus 50 equals minus X, and minus 8 equals minus X. The minus cancels the minus, X equals 8. So that's how we deal with it. So X now is equal to 8. So that means the students that, that participated in both are 8 students. You can choose to derive, put in your Venn diagram as well, and you also get the same thing. You can interpret. It's just that whenever if you're doing it with that Venn diagram this time around, there'll be nothing here. It's going to be X that'll be here. So when you want to get physics only, you say 22 minus X. When you want to get math only, you say 28 minus X. But this is the formula, and we're good. Shortcut, right? Now, Israel, for the one you mentioned, the one that's going to be outside the Venn diagram, let's take a question that deals with that. So let's say a survey of 100 students in an institution shows that 80 speaks Hausa and 20 students speak Igbo. Is that Igbo? Okay, yeah. Now, while only 9 students speak both language, how many students speak neither? You see this? This is away from the sets. So this one is going to be just outside in the universal set. So if we're calculating this now, okay, we're going to put in the universal set. The universal set here, it says a survey of 100 students. Now, there's 100 students in that survey. So our universal set of Hausa and Igbo is 100, right? But in that universal set, we are having some that, some students that they don't speak Hausa. That means they're not part of the universal set of Hausa and Igbo. So here we subtract the Hausa and Igbo because we don't know what that is. They're not part of it, right? So that is 100 minus 9. Thank you, John. Yeah, that is 9, correct. So for the universal set now of Hausa and Igbo, according to the question, the universal set of, thank you, Genevieve, Hausa and Igbo is what? 100. But because we have some that neither speaks Igbo or Hausa, that is, we're going to subtract it as X. I will explain that with the Venn diagram too, so we can have a clear understanding. So this is 100 minus X. Now we know that the formula will be the cardinality of Hausa plus the cardinality of Igbo. Cardinality of Hausa plus the cardinality of Igbo minus the cardinality of Hausa intersects Igbo. So let us get down to business. So this one now is going to be 80. We have 80 plus 20, then minus 9. And remember, this is 100 minus X. The reason why we're saying minus X is because it is not comprising of Hausa or comprising of Igbo. So the universal set will be that minus X. So we have, this is 100 minus 9, that is 91. So we have 100 minus X. So we can make X subject formula by taking X to the other side and bringing 91 here. So we have 100 minus 91 equals X, and X is equal to 9. Now, let me explain that in using the Venn diagram. So you can see what I mean. So we have Hausa. Okay. We subtracted. One second. We subtracted 100 minus 91. We just solved it here. The number of Hausa plus the number of Igbo minus the intersection between the Hausa and Igbo. That's what we calculated. Okay. And then we know that the X stays outside. That's what I'm trying to explain. Why is the X staying outside? For the universal set. So let's take it like this. Now the question says, let this one be Hausa and let this one be Igbo. Now the people that don't speak anything at all is X. We don't know them. It's just outside the universal set. Okay. The ones that speak both of them is 9. Hausa is what? 80. Igbo is what? 20. So we have, to get Hausa only, we have 80 minus 9. To get Igbo only, we have 20 minus 9. Sorry. We have 20. So now you can see the X that is outside. The universal set is 100. So because it is not comprising of, we cannot say Hausa then, if we're saying Hausa alone or Hausa complement, then we include, okay, Hausa complement will just be Hausa. So because of the X that is outside, that's why we say, okay, since if we say the universal set of everything, the universal set is going to be everything inside here, Hausa, Igbo, and the one outside to join. Everybody come together, that's X. All right. But since we're looking for the people that did not do both of them, so anything that concerns X, we move it to this other side. That's why we're having 100 minus X here. So it will now be the universal set minus X. Because it does not have any business with the Hausa, it does not have any business with Igbo. Those students don't offer anything. And then we're left with just Hausa and Igbo in the universal set. And we can now solve. So we can now use the formula cardinality of Hausa plus cardinality of Igbo minus the intersection. And we'll get our answer. So how we got 9? We made X subject of formula. That's how we got 9. We made X subject of formula. 80 plus 20 minus 9 is 91. And we have 100 minus X. Remember in mathematics, when you're moving to the other side of the equality sign, whatever sign that is here will change. So plus 91 will change to minus 91. And minus X will change to what? X. We're doing that so we can get the subject. We can make X stand on its own. That's the subject formula. And that becomes what? That is x equals 9. Okay. Do you understand that part? All right. So let's keep going. All right, so that is on 2 subset. We're about to wrap up. That is on 2 subset. We're about to wrap this class up. 3 subset. Let's deal with 3 subset. And then after that, we wrap up. Before we move to 3 subset, we have any? There's also a formula for 3 subset, and we'll be done. So do we have any questions? And anything concerning set, you just know that you know it. Yes, I can host physics. I also teach physics, but I need to. Oh, Chukwuemeka, you can ask question if you're confused in any part. Mondays. See that Monday, I'm very. I need to find my daily bread. Okay. So that's why I scheduled for now. Well, you have my contact, right? Yeah, so you can try to contact me because sometimes I take students anywhere. So online, offline, and places. All right, physics, maths. Yeah, we can try hosting for physics during the weekend. Yeah, we'll explain physics. Don't worry. I know it was kind of confusing for physics, but we'll break it down. There's no problem with that. Yep, you're welcome. Okay, so let's move into 3. You're welcome. Move into 3 subsets. After this, okay, no problem. Let's move into 3 subsets. Now, for any 3 subsets, there is a formula. 3 subsets is saying the universal set that the universal set of, if there are 3 subsets in a universal set, right? The cardinality of these universal set. Yeah, I would have loved to teach, but you see that daily bread. Nigeria of today is killing us. Okay, so, but I'll do my best. I'll do my best to contribute. We have the formula is, I'll surely do my best. The cardinality of A plus the cardinality of B, and then plus the cardinality of C. It's how you deal with 3 subsets. And then you subtract it from, this is a bit more complex, A union, the subset now, A union B, you subtract it from A union C, A intersect C, and then you also subtract it from B intersect C. That's the formula. So the intersection of all of them, you're going to subtract it. Then you add the intersection of them all. That's intersection A, don't worry, I will explain it. Don't worry, relax, Amina. Relax. We'll break it down. A intersect C, intersect B, intersect C. We'll break it down. I'll explain. Don't worry. Forget how long it is. When we start dealing with questions, you see that, okay, this thing is quite easy. Okay. So, when we start dealing with questions, you see it is quite easy. All right. So what you need to understand is I'll use the Venn diagram to explain it. When I set a question, I'll use the Venn diagram to explain it so you can understand what's going on. So first of all, in a community, let's take a question first so that we can relate this. I'm sure when you see the question and we break it down, you'll be able to relate. So let's take the question first. So let's say in a community of 160 people, 70 have cars. So we have cars there, 82 have motorcycles, and 88 no, that form, this is for 3 subsets now. Oh, I have to add the formula. That's the formula. That's the shortcut now. So we don't have to be doing Venn diagram. We just use that formula and we get what we need. So 20 have both cars and motorcycles. All right, 25 have both cars and bicycles. Wow. 42 have both motorcycles and bicycles. Now, each person rides on at least any one of the vehicles. First question is, draw a Venn diagram to illustrate. Since we're not going to be really dealing with drawing Venn diagram, I'll still draw it, but we'll use the formula and I'll explain the formula. Second question says, the number of people that have both cars and bicycles, but not motorcycles. And the third question says, how many people have either one of the 3 vehicles? All right. No thanks. All right. So let's deal with this. Don't worry. It's an easy question. Okay. So the first thing we want to do here is look at it. It says in a community of 160 people. The whole community is 1. So that means our universal set or universal set itself here. Start with universal set is 160. Okay, good. Now it says for cars, the cardinality of cars, 70 have cars. Just list out the parameters. What else? For the cardinality of motorcycles, how many? Cardinality of motorcycles, we have 82 have motorcycles. So that is 82. For the cardinality of bicycles, let's use that one as B. So, sorry, let's use that as B. Cardinality of bicycles, that's what, 88. Okay, now, it said 20 have both cars and motorcycle. So, cardinality of cars intersect motorcycle is what? 20. That's 20. Then it says here that, what else? 25 have both cars and bicycles. So cardinality of cars intersect bicycles. Cars intersect bicycles equals 25. And then it says 42 have both motorcycles and bicycles. So cardinality of motorcycles and bicycles equals what? 42. Now the question is saying here, we don't have people that have either one of the three. So let me see. Either one of the three, meaning that cardinality of everything together. C intersect M intersect B. So the people that have both cars, they have motorcycles, they have bicycles. That's question C. It says how many people have either one of the three. So we don't know that. So that is X. Now that we have that, we have that understanding. Do you have any question in these cardinalities I just listed? So I will break it down. Okay. Okay. So let's go forward. Now, if I'm to use the formula before I move into Helua, where are you lost? What part? What side? The beginning of the equation. All right, so the beginning of the equation, we just listed the parameters we have. It says in a community of 160 people, that's the universal set. 70 have cars. Look at the cardinality of cars. 82 have motorcycles. That's the cardinality of motorcycles. And 88 has bicycles. So that's it. Have bicycles. Then we have 20 have both cars and motorcycles. That's the intersection of cars and motorcycles. Then it says 25 have both cars and bicycles. So that's intersection of cars and bicycles to be 25. And then 42 have both motorcycles and bicycles. That's the intersection of motorcycles and bicycles. That's 42. And it says each person rides on at least one of the vehicles, but we don't have that information here. That means at least one of them. They have one. Okay, so the first question is draw a Venn diagram, which we're going to draw. Find the number of people that have both cars and bicycles, but not motorcycles, meaning that they have car intersect bicycles, intersect motorcycle complement. Remember when we're dealing with that? Don't worry, we're coming back to that. And then it says, the third question is how many people have either one of the three? That is the central, the one that's going to be at the central. Okay, so the first part we did was we're just trying to explain the equation. Do you understand? Okay. Okay. So let's have this to be for cars, or okay. What it says bicycles. Let's have this to be for bicycles. And let's have another one to be for, 1 second, delete this. Let's have another one to be for motorcycles. All right, let's go. So I'm going to go here. So let this be my bicycle. B, C for cars, and M. So for cars here, I have 88. For bicycle here, I have 88. For cars here, I have 70. For motorcycles, I have 82, right? According to the question. Then, how many have everything all together? We don't know. So that is X. Okay. Mhm. Yeah, John, that is correct. And then we say people that have motorcycle and bicycles. So motorcycle and bicycle only. So that is 42, right? For motorcycle and bicycle only. But we still have to subtract X because X contains everything. All right. So we have to just find motorcycle and bicycle only with C complement. And for car and motorcycles, we have 20, but this is going to be 20 minus X because we need to remove everything that doesn't deal with bicycles, just cars and motorcycles only. So we remove X, okay, minus X. And then for cars and bicycles only, so we have 25, but it's going to be 25 minus X because we don't want to deal with anything that deals with motorcycles, just cars and bicycles only to be at that part. Okay, and then the universal set here is, our universal set is 100. 160 rather, sorry. So we have the universal to be equal to 160. 160. All right, and now we move. So let's that's the Venn diagram. So we can get X, we can get the one at the middle using the formula. So let's use the formula. The formula is, let me now explain this formula. So if I'm to use this formula, someone said the formula was too long, but let me show you how it works. So if I'm to use the formula, let me just take the formula here. The formula is going to be the union of everything. That means what is concerned, union of everything, all the sets that is mentioned, that's the universal set, equal to the cardinality of the first one, plus the cardinality of the bicycles, plus the cardinality of, motorcycles, and then we start subtracting the subset, minus the cardinality of, let's say, C intersect M, minus the cardinality of B intersect M, minus, don't worry, I'll just break it down. You'll see what it represents. B intersect, okay, we have C intersect M, so this would be B intersect C. Okay, and then we add plus everything that's at the middle. We add it. C intersect B intersect M. So that's the formula for 3 subsets. So what you do here is, this is 160. This here is 160 equals the cardinality of cars. So we have 70 plus cardinality of bicycle, that's 88, plus motorcycles, that's 82, then minus cardinality of just C intersect M. So for C intersect M, where is that? Yeah, that is C intersect M. So that is 20 minus X. So I have 20 minus X. When you're applying the formula, though, whenever you're applying the formulas, you actually really don't need to put the X. I'll show you why. And then we have minus C, B intersect M. B intersect M is 42 minus X, because the X, they will cancel out. And then we have, so this is minus 20 minus X, 42 minus X, then minus, what else? B intersect C. B intersect C is 25 minus X. So we have 25 minus X. That will cancel out. And then What else do we have? Plus the intersect of everything altogether, that is x. That's just it. What you do here for the formula breakdown, just take this one, add it with this one, add it with the third one, then you start subtracting the intersect. You subtract what is here, minus what is here, minus what is here, then you add what is in the middle. That's how you do it. Okay? You take this, add it with this, add it with this, then you start subtracting the intersect. You subtract what is between B and C, what is between B and M, and what is between C and M. Then you add what is in the middle. That's what the formula is saying. Look at it. We are at 70, 88, and 82. The main subset, 70, 88, 82, you add all those ones together. Then you start subtracting what is between 88 and 70. Put it here. What is between B and M? What is between C and M? That's what you subtract. You subtract those ones, then you add what is between everything all together. That's how you deal with 3 subsets. Now, the scary part is, the main part rather is, when you're applying the formula, no need to put this minus x. I'm going to explain why the minus x, there's no need for minus x there. But if I don't put it now, some people might get lost. So we have 82. If I open this now, this becomes minus 20. Okay. Minus 20 plus x minus 42 plus x. So there's a reason why we don't put it minus 25 plus x. When you open that formula, and then we have a plus x here. So let us add. I just want to show you something. Let's add 70 plus 88 plus 82. So if we collect like terms, let me just arrange the number and collect the like terms. This is pure maths now that we're dealing with. So 70 plus 88 plus 82 minus 20 minus 42. Don't worry, this is the last part of sets. After this, you go and take one chilled Coke. Minus 25, and then plus x, plus x, plus x. Ask your question. You have any question? So here I'm just collecting the like terms. I'm arranging it. So number to number. Okay. Okay, so 70 plus 88 plus 82. That's going to give us, let's see. Yeah, that's 240, right? Minus 20 minus 42 minus 25 is 87. Then we have plus 3x. So this is where the error comes in. This now is going to give us 153 plus 3x. Now, in order to make your work easy, when you're dealing with
Should be 4x.
Sorry?
Should be 4x.
Yeah, 4x plus x. There's another x here. So 4x. So this is where the issue comes in. That's why I want to clarify something. When you're using the formulas, no need to put in the subtraction. The reason why we're putting this 20 minus x here is because we don't know what x is. When you're using the formulas, no need to put the 20 minus x and 42 minus x and all that. You don't need it. When you're using the formulas, just follow what is stated here. Follow what is stated in the question. Don't put it inside the formulas. If you put it inside the formula, you're going to have error. And that's a mistake you make. If you're using the formulas, just go straight. Formula is easy. follow the formula, put in your numbers, boom, find what you need. So here we're going to have 160. Let's make x subject of formula minus 153 equals 4x. And this is where the whole issue starts, because now this is going to give us 7 equal to 4x. And our x cannot be 7 over 4. So the reason is because we included minus x inside the formulas, or we're subtracting inside the formulas. So whenever you're dealing with the formula method, do not include, do not add all this addition. This one is for Venn diagram, so you can get clarity. But do not add all this minus x, minus x, minus x, and all that inside. No, don't do that. Just put in what you have, put in your parameters, and solve your question straight up. So let's now make this interesting. So all this minus x go away. Now the right way to apply the formula is just this. So you just apply what you have. Okay, all these x, take it out. And then this plus x is the one at the middle, remember. So that one will stay there because it's part of the formula. Okay, all this x, clear. So we just have plus x there. That's the way to apply the formula. If not, you end up making mistake. And x is equal to 7 at the first part. X there will be equal to 7. So that means there are 7 of them that are dealing with the number of people. Okay, there are 7 of them that study either one of the 3 vehicles. Sorry, they have either one of the 3 vehicles. They are riding either bicycle, cars, or motorcycle. X is 7. Now that X is 7, the question is saying, find the number of people that have both cars and motorcycles. Both cars and bicycle, not motorcycle. Cars and bicycle is 25 minus X. So you come here, 25 minus 7. The reason why we're subtracting 7 is because inside 7, some people are having, yes, Genevieve, some people are having motorcycles. Yes, Genevieve. Are you trying to talk? I hope your mic is not mute.
Oh, can you hear me?
Yeah, I can hear you now.
I think 20 minus 42 minus 25. How did we get 87 here?
Oh, okay. This is when you're subtracting, don't forget the signs.
Okay.
Okay, so
Minus
let us
20 minus 42 minus 25. Oh, we have minus 87. Okay, I got
correct.
it.
There's the signs that are the signs. Yep. So question C is 7 and B is 18, because we removed everything that concerns motorcycle from that equation. So that is how to find the X. That's how you deal with 3 subsets. There are actually more questions, but probably what I'll do is I'll put it in a document and I'll send it to those here, or I'll put it in the group Lagos software and any other cohort group that will need it. So I'll be sending out the whole thing. So that is actually sets. That's like sets. Okay. That's actually sets, or dealing with sets, or anything that has to do with sets. That is set. Now, you can have that understanding of set. Then, but the reason most people got confused on the test is because Mr. Holloway, what he did was, after he did the Venn diagram with 3 sets, this is with 3 sets now, but you see, it's kind of a bit shady and though he made some explanations, but after he did this, all right, using real world situation, this is 3 diagram set. Just use the formula, use the same formula we used, and solve your answer for questions like this. Use the formula. So after he did this and he explained, he went into what we call, this now is called mapping and functions. Not, though it also is also like a branch of it. It touches set, but set is just like a borrowed brother inside of it. So this is mapping and function. That's another topic entirely that you need clear understanding of. But you can see the notation of sets and all that is there. But this is mapping and functions. The inverse of the functions and all that is under mapping and functions. So we can treat that as well. It's also part of what we'll be doing in quadratics. We'll be touching functions in quadratics. And yeah, we'll start with functions, get into mapping, then relate how functions touches quadratic equations. So that's going to be our next class after the next break, if you're still available. I told you it's a class marathon, so peleo, or those that are already tired. Okay, the 18th answer, Amina, is for question C. Here, it's for question C that says, question B, yeah, that says, find the number of people that have both cars and bicycles, but not motorcycles. Yeah. So it's for that. Okay, so are we ready to, this is my Google. I hope we'll be able to receive this space. Anyways, it's going to be online, so the amount of gigabytes you used to watch, we watch the class, because we're going on a crazy marathon. Give us questions to solve for the break. Make I sharp my brain small. Okay, all right, let me set questions. And during the break, once we start break, I'll type those questions out and you can use it. Are we ready to go on break? So I can put it out here. What's in gig? Okay, well, it's one thing with Open University. Most of our things online, we're the ones with cloud computing, we're the ones dealing with the cloud mainly. All right, so if we're ready to go on break, let me set the timer. That's going to be 30 minutes. We'll move into mapping and functions, and then we drive into quadratics. Okay, so let me just set this to, we have 30 minutes, and then I'll set out the questions. And yeah, please, do we have any person that just joined us here in this second, after the break, after the first break we had? Anybody that just joined? Like, did anybody join us later? Okay, so for those that just joined, I'm going to only take 8 minutes of your time. I know I kind of like talk too much, but I need to talk too much sometimes. So I'm going to just take like 1 second. I'm going to take 8 minutes of your time. I just need to, so the break has started. Then after the 8 minutes, I'll use the remaining 5 minutes to, set the questions. Then the remaining 17 minutes, you can use it to enjoy yourself and all that. Okay, so let's yeah, I'm going to share something. It's just a little brief about myself. So if you just joined, pardon me, I'm going to talk a little bit. I'm going to talk too much a little. So please, Bele. Yes, we can go on break now. Our break has started. So we can go on break, or you can stay and wait for the questions. I'll also drop that soon. All right. So yes, this is me, and this is actually what I do. Hosting a STEM club, and for this, For the STEM club is actually science, science, engineering, technology, and mathematics. That's what we actually do in the STEM. All right. So science, technology, engineering, and mathematics club. So it didn't just start now. We have on our agenda. Yes, pardon my music. So the agenda here is agriculture, technology, and power generation. That's electricity. And that's what I'm training most students for, or the next generation of students that are under my wing. I need to go national, Sha. Strategic placements to enhance education of tech programs, meaning we have ways that we're going to get into tech programs and access these tech courses and give a lot of people access to it free of charge and certify them so we can build a productive front and recreate tech programs, distribute skills to boost productivity for the country, engage in power productivity engineering, and ensure the education gotten is used for national development. So meet me. This is me. I'm Gideon Wakama. I'm also a student of Miva University. I'm not a lecturer in Miva. Actually, I teach, and I've been teaching for 9 years now. I'm the lead and chief operating officer of and mathematics educator, STEM advocate with over 9 years experience. I specialize in secondary school students, candidates, and university students in mathematics, physics, chemistry, while fostering critical thinking and innovation. I'm the founder of Education Asset Development Initiative. Learn Academy is my online tutelage that I just opened as of 2 years ago, and Rebound Foundation, also a charitable organization for scholarships funding for schools in Federal Technical College, and leader of STEM Club Nigeria in collaboration with the Innovation Center Africa to develop impactful programs, competitions, and projects that empower young learners, blending academics with real-world skills, technology, and creativity to inspire future problem solvers. Don't worry. If you go to Instagram and type gidi.wakama, you'll see all my portfolio there. And we have Mazi Michael Ihekwereme. He's the lead engineer. He's experienced in mechanical engineering and electrical with over 6 years in the field. With the past 4 years, he has been dealing with renewable energy and power generation, and also supporting installation process across the nation. He's passionate about educating the next generation and empowering businesses and individuals with sustainable, reliable energy solution for growth. So if you need that solar installation in your bedroom, in your one room, Michael Ihekwereme can help you with that installation at an affordable price, something that can, be good for you. At least you power your laptop systems 24/7 without having to breathe in lead acid batteries, things that are safe for you actually. And then we have Victoria Chiffon. She's a secretary and virtual administrator, and with 3 years of experience, she enjoys talking to people. She helps to facilitate our coordination and keep communications. And then we have our media, our member assessment review officer, Gift Olushola, a media coordinator, and she helps to assess every member that is in the club. So for assignment, for follow-up, track your progress and all that, she's in charge of that. Okay, so the STEM Club was formerly Mathematics Club, which started in the year 2019. What I do is I go into communities and seek for potentials by building a platform where they can be better and develop themselves. So since 2019, the target is the future, and that is the children and teenagers. We need to catch them young before they become solid rock on the mentality. So in the year 2019-2020 academic session, my first scholarship was issued in my math club after I hosted a regional mathematics competition in 2019. It was the first of its kind, and the area was lacking of social impact. So I initiated a potential development initiative and invited schools to participate in what is now known as the zonal competitions. It wasn't easy seeking for sponsors, as most of them were not after the impact of children or next generation. So I raised funds myself. I did extra jobs, and I used my skills. I taught the philosophy that if I, a Nigerian, can sacrifice for you, you can sacrifice for others. Then you can do it for the nation. Right? This mentality is what I seek to drive in this movement. I didn't just go into mathematics alone. I also touched sports. I touched athletics for children and teenagers who are gifted in that aspect. So creating competitions, communities that will grow together, as well as taking my boys out for other competitions to get exposed and noticed. Just in the span of 2 years, we grew from 7 to 40 players all free in the academy, because money in communities are like a barrier, and we don't invest. If we don't invest in these initiatives and infuse money, we can't reach people or see the real talent. So we as youths can create something for ourselves through this initiative of coming together and working together. Yep, as of 2021, 2022, we won multiple awards in the Football Academy, touching and impacting lives in every direction and applying the same philosophy. If I can do it for you, you can do it for others. Now, there are some of us were recognized by the Habit brand, and we're giving special awards for the Habit brand. Yeah. So fast forward to 2024, there's still a lot, but fast forward to 2024. Where I transformed the mathematics club and debate club into just one demanding unit, which is the STEM club. I fostered into getting into communities and developing the next generation in agriculture, tech, and engineering in power generation. In this part here, we made our first power bank, and in 2025, we progressed that power bank into a solar power bank. And then just last month, we were invited by Federal Technical College to showcase our works from the STEM Club Lagos to see how teenagers are instilled with tech education and engineering on renewable sources of energy via engineering. Now, the agenda is to ensure we can reach out to at least 5,000 youths by next quarter of the year, and we create a platform where they have access to advanced tech courses. So we'll build a productive force in the market. I also want to create more competitions to promote unity in the knowledge of agriculture, tech, and engineering, and promote communities and competitions that can bring a combined front in these aspects. Now, you might be asking, what is our strategy? I believe that the youths can do anything. All right. So the strategy is to train some teenagers in these platforms like Code Academy and Data Camp, and then they transform these courses. They in turn will transform these courses into modules for our Nigerian citizens to gain access to free of charge. And then we get certified by collaborative organizations like the Innovation Center Africa, which is ventured into tech. I believe that the youths can do anything. So if they really set their minds to it, they will achieve it. Ever since the answers, we have proved that unity can conquer, and to make a change, one needs to build and not venture in passive aggression like protests. We need to build to make the change, and we start by building our communities. So the fundraiser target. All right, the fundraiser target is to train is $3,000 to train some youths and teenagers and transform these trainees into courses. So then in turn, I'll impact them with how to set up curriculums. So as they're learning, they're giving out, they're teaching as well. Then we will create it into courses, and then it's free in the productive market after we've gained from first-hand United States experience platforms. We get the expensive platforms and train our people, then we recreate, we give back to the society and make it cheap or free. Now, if you feel this is something you want to be a part of, a united front, you can reach out to me via g.wakama2314@miva.edu.ng. But if you want it to be personal, this is my personal email, gideon.wak@gmail.com, and that is my number. There's also Instagram, gidi.wakama. You can see me on LinkedIn, Gideon Wakama, and the likes. Yep. And you can see other things that I do there. So any part of donations, can reach out to me for further details. If you want us to partner, if you want to share ideas, if you want to drop into whichever thing, you can partner with me. Okay. So thank you very much for that. I know I talk too much, but I just want to use this as an avenue to give out to what I do, raise funds, and see how we can create the next generation. All right, so back to our time. I think that is 10 minutes. I think I was a bit slow there. Maybe I need to drink water. Okay, so let's set that question. Hello, Genevieve. I need to set the questions. Mhm. All right, so let's see this. Oh, I'm already putting the questions down. Sorry. This is the questions. I'm already typing it. And one more. Ife, do you still have problems with this that we did? Okay, you started with us from the beginning? If you have any problems, you can DM me. Probably we'll see how we break that. Okay. All right. Just you can DM, and that is. So we have less than 13 minutes left for break. You can go stretch yourself out before we come into mapping and function. Statics, stretch, 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 and we're back in 13 minutes. 13. Okay. This is the, okay, less than this. So All right, so we have just less than 7 minutes before the break um, is over. So 1 minute time, I'll call you back to class and then continue. All right, so we have less than 20 seconds. So someone said there is something missing here. 8 speaks Igbo, Hausa Igbo. 11 speaks Yoruba and Hausa Yoruba. Okay, this other one, and 6. And 6. Right. Okay, it's meant to be 6. It's meant to be 6. Joshua, so that is 6. That's the last parameter. Thank you for acknowledging that. All right, so let's get to it. Let's get to business. Welcome back. Welcome back. Welcome back. Okay, so for those that are still, some of us still survived the marathon. This is like, we started at 11, right? Wow. Gone like 4 hours. This is so 3 already. And you're still here. You need to applaud yourself. You need to clap for yourself. That's great. You have energy. You have energy. Okay. So mapping and functions. That's what we're going to treat. That's what is here. So you can understand this clearly. A function, and then we move to mapping and functions, inverse of a function and all that. Once you understand that, we move to quadratics. Okay. So let's go ahead. Genevieve, you said maths. Almost. What happened to maths? I want it to be that if you're in this class, you actually understand, or you're taking something, at least there's going to be an understanding of little concepts. My main aim in this class is to break down. Okay, is to break down. Of course, I'll give you the answers. Before we treat mapping and functions, I'll do that question first. So the main aim is to break down the concept so that we can understand clearly. So let's get into mapping. Before that, let's treat this part here, which is the first question. Okay, let's deal with the first question. All right, so the first question says, in a science class with 80 students, 40 students passed mathematics. So I think we all have that question, right? Because I want to solve at this part. So let's put it this way. All right, so it says, in a science class with 80 students, 40 students passed mathematics, 45 passed chemistry, and 30 passed biology. Now, 20 passed, so let me put out the cardinality first of all. We're dealing with 3, right? So I have, first of all, my universal set. So what concerns mathematics, chemistry, and biology. I'm just going to use a formula. Then it will be equal to the cardinality of mathematics. Remember the formula, plus the cardinality of chemistry, plus the cardinality of biology. Then we start subtracting their intersections, minus the cardinality of, that's maths and chemistry, minus the cardinality of math in biology, minus the cardinality of chemistry and biology. And then we add what they have in total, plus the cardinality of what they all have in common. Math, chemistry, and biology. Students that have that. Now, according to the question here, it says 3 students did not pass any of the subjects. So that means our universal set here is going to be 80 minus 3, the same way we did the last question. So that means it's outside the box. So it's going to be 80 minus 3. And so let's impute our parameters. We have 40, we have plus cardinality of chemistry, that is 45 that passed chemistry, and then we have that passed biology, that is 30, right? And then we can start subtracting the intersection. So to subtract the intersection, we have that for maths and chemistry, they said 20, pass both maths and chemistry, so minus 20. For that of maths and biology is 12, and those that passed chemistry and biology is 8. And then it says the what is common in those that passed all the subjects. We don't know that equation. They said the question said we should find how many passed all the subjects. So plus x. This is it here. Those that passed all the subjects. So we don't know that. So that is x. And then we solve for x. So this is going to be 77 equals 115. Yes, Yusuf.
Good evening. Hello, can you hear me?
Yes, I can hear you. So we're already in the evening. Wow. Time travels.
Yeah. Okay. So apart from this, so I'm be trying to be join this meeting. Okay, revisions. So actually, I don't guess understand the sum of discussion we talk it past tense. So actually, the network on today is too low. There are a lot of people will not join the this discussion. But even me, till the morning, 11 o'clock, I mean to start this. Um, can you hear me?
Yes, I can hear you.
Okay, till the morning to be start this presentation. I'm saying this
Okay.
gathering. The network is not working good. It's not working clearly. So that is why for not to get understand for this what you are talking, because I
Oh,
need to you need to know this fluent direction, because that even like this lecture, it is very important to us. If you
yeah.
get what you or understand PDF, so you can't understand fluently clearly, but even do to understand this. This is a very very important. Have do you have a what offer day can be retrieved, or this day it is okay? You know.
Okay. So the session is recorded and it
Okay.
will be sent to you. I'll put it in the
It,
groups. I don't have your personal emails. You know, I'm a student as well. So I'll just put it in the Lagos group. I'll put it in software engineering department. I'll put it in cybersecurity, in cohorts. I'll put it everywhere and all that.
okay.
So everyone will have access to watch the recorded class and all that. So with documents and all. So
This I recorded.
sorry. Yeah, it's recorded. The meeting is recorded.
Okay, thank you very much, Mr. Gideon. Is it
Yeah,
Gideon?
Gideon.
Okay,
Yeah, Gideon.
Gideon. Thank you very much for
You're
this.
welcome.
No.
You're welcome.
Okay,
All right,
go
Genevieve.
ahead.
Yes, I think that was my
I
error.
think that was my error.
I apologize for that. That should be my error. Apologize. So there's meant to be 8 in that question. That is for. Oh, that's what Joshua was telling me in my DM. That there is a missing. I also went to go and stretch my leg. Sorry. So this is 115. No wonder you did. Okay, we have a hot mic. No wonder you said no wonder you say mass and problem. So sorry about that. Now it's good. That means you know what you're doing. That means you understand the concept. You know exactly what you're doing. You understand the concept and all that. So that is very good. Meaning that you know there's an error in that question and you're able to detect the error. Knowing that yes, I'm proud actually. That yes, you did something that this thing is not complete now. You actually know it is not complete. So that's good. So 77 minus 75, yes, the answer is 2, Genevieve. You got it right to be 2. So, okay. So x equals 2. So 2 students passed all the subjects. So yeah, x equals 2. Right. So it's very, very, it's a good thing you're able to detect that. All right. I know. Okay. All right, let's see the other one. In the survey, out of, first of all, let me ask, what did you get? What was your answer in the other one? In the survey, out of 100 patients who reported at the clinic. Six. Okay. All right. Who else got 6? Is it there was not 8 in the first one or the second one? Oh, in the first one. Yeah. We just talked about it. Um, 40 plus 45 plus 30, 40 plus 35 plus 30. I think that is 115, right? That is 115. It's not 135. Okay, Mark.
Okay, Mark.
All right.
I can't hear your screen.
You can't see my screen?
Okay. Yes.
Okay, try to log out and log in back.
Okay.
Okay. Let's do that. Yeah, this is 30. Oh, this is 30. According to the question, 30 pass biology. It's writing 30. Pardon my handwriting. It's 30, not 50. All right, so the second one says in a survey of 100 patients. Okay, so we have 100 patients in the survey and okay, 6 as well. All right, let's solve it together. Of the 100 patients, let's take the cardinality first of all. So we have a cardinality here. Cardinality of everything all together. That's, let me put it. Sorry about that. So the question called for how we can solve these 3 subset problems in Venn diagram. So first of all, let us represent it. All right, the entire universal set here is going to be the F. That's the one for, or is it patient in the clinic? Fever. So let F be for fever, let S be for stomach, and let I be for injury. So we have F union S union I. So this is going to be the universal, and that is what 70, right? That is 100, right? And then how many complete of fever? So cardinality of fever, that's going to be 70. Someone got 3. That's correct. And then cardinality of stomach, that's going to be what? The cardinality of stomach, that's 50. And the cardinality of injuries, that's I, that's what? That's 30. Now, all the 100 patients had at least one of the complaints, and 44 had exactly 2 of the complaints. Okay. So if we're going to apply the formula now, it says one of the patients here. If I'm applying the formula, this is going to be 100 equal to 70 plus 50. Like we just put out all the cardinalities first, right? Plus 30. Then minus. Now it says the cardinality, at least one, all the 100 patients had at least one of the complaints, and 44, so one of the complaints, and 44 had exactly 2 of the complaints. So because of this, the one of the complaints is just our normal X, like what we're looking for at the middle. So for questions like this, I'm going to use the Venn diagram to explain it, because the answer is scrolling between 6 and 3. If you got 6, relax, don't worry, don't be scared. Don't be scared of Chukwuemeka. Okay. If you got 6, relax. I'm going to explain it here in this Venn diagram so we can all see it together. And if you got 3 too, relax. We'll see why you got 6 and we'll see why you got 3, because you're actually correct. Okay, so let's put it like this. Let it be the Venn diagram. So let this be F. I'm going to break this down. F equals 70. Let this be S equals 50. And let this be I equals 30. Oh, let me make that I well, so you don't complain about the handwriting. Okay, good. And then what is inside here? Let it be X, right? The ones that had 3 of them. So let it be X. What is X? Now, in order to get both for fever and injury, we have fever and injury. Okay, let's put it this way. They didn't give us that information, right? They just said had at least one of the complaints, and 44 had exactly 2 of the complaints. So we're going to represent it using our mental maths, right? So let it be for cardinality of fever and injury. So there's going to be cardinality of fever and injury. Let this one represent Y. Let us say that cardinality of fever intersects stomach. Let this one represent, give me a variable. Yeah, okay, let's say K. That's what is between fever and stomach. Then cardinality of, let's say stomach and injury. Yeah, the last one, right? Let this one represent B. Okay, C. All right, C. Okay, let's represent C. Thank you. So for cardinality of fever, between fever and injury, since they didn't give it to us, we'll just say this will represent Y. So this is, to get what is here, that's Y minus X. And we're subtracting what concerns it. And for fever and stomach is K. So this is K minus X. And for stomach and injury is I. So this is C, So this is C minus X, sorry. So when we're imputing our formula here, okay, then it also said that when we combine everything together, the question here is at least one of the complaints. All right, patient had at least one of the complaints. So it means we're going to combine everything there together and to see what it's going to give us. So 44 had exactly 2 of the complaints. So everything here, F and I, F and S and I, They're all 2, 2, 2, right? They're representing 2 and 2 and 2. So the question, when you hear something like at least, you're able to detect and you're able to deduct it that, okay, for fever and injury, I have y minus x. So anything that concerns 2. For fever and stomach, I have k minus x. For stomach and injury, I have I minus x. Okay, anything that contains, let me come again. Okay, so the question says, all the 100 patients had at least one of the complaints, right? At least one of the complaints means it's everything. Like one of them is having everything. That is X. And then 44 had exactly 2 of the complaints. So that means the ones that concerns 2 of the complaints here are the intersection between fever and injury, stomach and injury, fever and stomach. That is the Y minus X, K minus X, C minus X. That's the one that concerns anything there. All right. So what we're going to say is we just equate it. The one that concerns Y minus X, that's the 2. This one is touching for just 2 of the sets. K minus X is touching for 2 of the sets. And the other one is C minus X. It's touching for 2 of the sets. So C minus X. All right. So if we put this all together, if we put it all together, Y minus X plus K minus X plus Y minus X plus K minus X plus C minus X. What's that going to give us? So we're going to have Y plus K plus C minus 3X. This one now is for what is for things that just happen to be what that is concerning with at least 2 of them. So I just brought out that formula so you can understand. I brought out everything that concerns 2 illnesses: fever and injury, fever and stomach and injury. Everything that contains 2, 2, 2, 2, 2. I brought it out together, and that's the equation there: Y plus K plus C minus 3X. Okay, and then it is telling us that all these ones here, okay, all these ones here that have at least 2 of the illnesses is what 44 of them are having 2 of the illnesses. So when we combine them together, it is 44 minus 3X for that part. Okay, so according to our equation, all right, according to our equation here, when you say, remember how we used to put in our formulas where we'll say the cardinality, all the cardinalities, then minus all the intersections, then plus what is at the middle. That's the same thing here. All the cardinalities, 70 plus 50 plus 30 minus all the intersections. We've calculated all the intersections to be this. That's minus 44. Sorry, 44. That's 44 minus 3X. Then plus everything that is at the middle, and that is X. So this is a very technical question. I hope they don't even bring it out in exam. So it's something like this. All right, it's a very technical question that you can you just read it like all the 100 patients had at least one of the complaints, that is X at the middle. X at the middle, at least one of everything, that is X. And then it says, and 44 had exactly 2 of the complaints. They didn't give us the value for that. They just told us 44 had 2 of the complaints. So everything that concerns 2 of the complaints, this, and this, yeah, all equal, added together is what? 44. Okay, added together is 44 minus 3X. And that's what we have here. So we can now start solving. We can now say 100. So let me solve it down here. We can now say 100 equals to 70 plus 50 plus 30. That's going to give us 150, right? Yep. So that's 150. Then minus 44. minus 3x plus x. And this is 106 minus 2x. And this is still 100. So for those that got 6 is because when we do this, so this is 100 minus 106 equals to negative 2x. So this is negative 6 equals negative 2x. So minus, we cancel minus from both sides, and we divide both sides by 2. So this is how x is equal to 3. But some just got x equals 6 because you didn't understand that question. Like, that's a technical question. It's meant to be a brain teaser. Okay, it's meant to be a brain teaser. So they should not do. Wow, yeah, Chukwemeka, you did it very well. Very well. So you're able to deduce that. So yes, and the last one, what was the answer for your last question? Someone got 3, right? Yeah, 3 is the answer for the last. It says calculates the value of x. That is 3. Yep, 3 is the answer for the last question here. The Lord is our shepherd. Of course. Of course. Well, that is set. That is set. So let's touch mapping and functions now. Of course, the Lord is our shepherd, Genevieve. Let's touch mapping and functions. Let's touch mapping and functions. So this is another interesting part. But he combined them all into MTN. Oh, sorry about that. Sorry about the network. MTN is really dealing with us in Nigeria. Like, really dealing with us. Data now is equivalent to data is equivalent to house rent. You must be rich to get Starlink. Wow. Okay. Thank you, Praise. All right. Mapping and functions. Yeah, let's deal with mapping and functions. First thing you want to understand, mapping is simply an association or relation between two sets. That is mapping. Okay. Now, some of us not get 5G phone. I beg. All right. Mapping is simply an association or relation between two sets. So this is how mapping is. Okay, so let's say I have, let me get an oval shape here. Let's put this shape. It's like a mirror. Okay, so let's say I have, let S be like the set of cars. Benz 190, 505, and Camry. So let me just type that here. Just see how easy mapping is. Okay. So you understand the functions. Let S be the set of cars. Take for instance, and this set of cars should be Benz. Let it be 505 Peugeot, and let it be Camry. Not our typical kind of cars, right? And let T be the set of car producers. Like, let's say we have the Peugeot Let's say we have the Mercedes. Just get camera. Let's say we have the Mercedes, and let's say we have the Benz. We have Toyota. Okay. Then there is a mapping which associates this mapping here. There is a mapping that associates f, the function of, this is where function comes in. The function is just giving a statement, all right? The function of s, okay, is mirroring t, or s is directed to t. Or you can put it like this: s has things, or s is also a subset. That's a function meant to be a small f. F is also a subset. So when you see it like this, you just know that, okay, it's a subset of t. All right, so for s here, we have, let this be s, and let this be t. That's why they joined the mapping and functions in sets. So let this be Benz 190. Let this be 505, and let this be Camry. Then let this be Mercedes. Don't mind my handwriting. You get the gist. Let this be Peugeot, and let this be Toyota. You shall get the gist. Okay. All right. So what is mirroring? Benz belongs to Mercedes. It's mirroring Mercedes is a subset. They belong together. 505 to Peugeot and Camry to Toyota. So the S that has the Benz 190, has the 505 and Camry, is called the domain. While the T, all right, is called the domain, while the T is called the codomain. One is the domain. One is the domain. The other is the codomain. One is the codomain. So this is codomain. Okay. One is domain and one is the codomain. And that is what mapping is. In mapping, you have a domain, and the codomain is mirroring what the domain entails. It's mirroring what the domain entails. Let's consider another mapping. Let's consider something. Let's consider this. I'm going to give you another one here so you can understand. So let's put one here. And let's put another one here. Okay. And let this be P. Let P be the domain. 1 second. So P is the domain, and let this be K. K being the codomain. And let's say we have P to be A, B, C, D. And let's say that K has elements. K elements is 1, 2, 3, 4, and K also has 5. All right, so we can just track the domains together. We can, 1 second. We can track the domains together. So A to 1, B to 2, C to 3, D to 4. Okay, we track the domains together. So something here, you can note that all elements of K are paired or related to P. All elements of K are paired or related to P. So the domain of the mapping here, the function domain of the mapping here is, the function here is F is the set of A, B, C, D. That's for the domain, right? Now for the codomain, the function of f here, f means is a statement, okay? What does it represent? Is 1, 2, 3, 4, and 5. That's for K. Now, the image, or what you call the range of the mapping, when you're asked for the image or the range of the mapping, you just look at, since you have the knowledge of sets, you look at, okay, what is actually contained in the codomain that matches with the domain. And what is contained, this is called image or range in mapping of functions. So the image or range of the mapping is 1, what was paired, 2, 3, and 4. That's what was paired. Those are the only pairs that we have. That's the image or range of the mapping. Do you understand that? All right. So we have two sets. One is P and one is K. P has 4 elements and K has 5 elements. This is called the domain. P is the domain and K is the codomain. Now, P, the elements of P matches the elements of K, but one is left out, which is 5. Therefore, the image range of this entire set is just 1 to 4, excluding 5. That's what it means. So we can say, okay, let's take another one. Let's say we have a mapping and a function. So the codomain is a set of real numbers. So the function is the mapping where the codomain is numbers. Let's say we have something like this. I want you to just understand the main concept of this mapping. Okay. So wait, before we move to that part, we have what we call the injective, surjective, bijective, and composition. It's still the same thing. But before we move into that part, I need you to clarify that you understand this before we move into the next part. How we got the image and range. All right. Okay. So now let's say we have another thing like this. Okay, Avio. Let's say we have another thing like this. And let this be H. And let this set be L. Now the function where the codomain is real numbers. So this should be real numbers, 1, 2, and 3. And let's say we have H to be A, B, C, and D. But when we're pairing this now, the question is now pairing it this way. 1 to A to 1, B to 2, likewise to D, and then C to 3. So there is a I mean, relax, I will explain it. Okay. Okay. So I'm just look. First of all, just listen for this first part. This first part is just breaking down the mappings and how the mappings are going to be represented. That's all it is doing. When you understand how the mappings are going to be represented, first of all, this one now is telling us the image or range. This one is telling us the image or range. A to 1, B to 2, C to 3, and D to 4. Telling us that every element of P here is paired with elements of K, excluding 5. So the image of this mapping or the range of the mapping is just 1, 2, 3, 4. because that's what is paired to P. It's the codomain that we use to read the map. Okay? Do you understand that part? Okay. Now, in this side here, okay, we have a function of, let's say the function is H being paired to L. Yes, Genevieve?
This A paired to 1, how are we supposed to know the one that is to be paired with each other? Are they going to give us that in the question to know what we're going to pair A to, or what we're going to pair 1 to, or B to?
Yes, in things like this, you'll be given the pictorial representation. So they can just give you this, and you'll be able to read the map. So they do
Thank
this. Yeah, this is what they'll give to you. Don't worry. The one that deals with question where you have to interpret yourself, we're coming to that before you get into functions. All right. The function is actually a very wide part, but that will lead us into quadratics. So let's deal with this. Now you guys, you all have the understanding of sets, and I'm very happy for that. Now let's also have the understanding of functions, mapping our functions. So a function is the codomain here is L, right? And this function or mapping, this function is a mapping that is acceptable since every element of the domain is uniquely paired to an element of the codomain, which is L. Now, in this other one here, all right, there is one other element here that is not paired. So most times the function, this kind of function will not be acceptable. It only has an image range of 1 to 4, but there's an exclusive 5. But you see this one here, everything is paired. Everything is paired. So one of them is accepted as mapping, all right? One of them is accepted as mapping and the other isn't accepted as mapping. Now, the only time it will be accepted as mapping is when the first mapping here, all the elements in the first one are uniquely paired with something in the second one. That's when it is acceptable. All the elements in the first one are uniquely paired with another in the second. So it is acceptable because every element in the first one is paired with an element in the second one. Now, what if I have an element like this in the first one? Let's say this one is L and T. I have another one here. Let's put this here. And L and T, right? And for L, we have A, we have B, we have C, and we have D. And let's say for T, we have 1, 2, 3. 1, 2, 3. Now we pair A, we pair B, we pair C, but we don't pair D. This is not accepted. Why? Because all the elements of the first set is not uniquely paired with the elements of the second set. So it is not accepted. This is not mapping. This one is not mapping. Okay? For the mapping, it has to be paired or it has to be associated with another one. Every element has to be paired. That is for mapping. Yes, King.
Me.
Yes, King.
Can you hear me?
Yeah, I can hear you now.
So what I'm saying is that from this other diagram, the one by our left now, you are saying each, like the domain must be paired to another domain, to the codomain. on the other
Yes.
diagram. Okay.
Yes. It must be uniquely paired to the codomain. Now, if you look at this here, B is paired to 2, and D is also paired to 2. They are uniquely paired. Okay?
Okay. Yeah.
Yeah. Now, what if B was paired to 1 and the same B is paired to 3? That is not acceptable because, okay, let me put something here like this. Let's say we have U and we have V. Okay, just check this one out. And check this out. And we have something like this. Now, for this one here, for you now, we have A, B, and C, A, B, C in the domain. Now for B, we have 1, 2, 3, and we have 4. Now let's say A is paired to 1. The same A itself is paired to 3. Then let's say B is paired to 4. And let's say C is paired to 2. Now, the error here is A is paired to 1, and the same A is being paired to 3 from the domain. Normally, it's meant to be the domain paired to the codomain, right? But if one of the domain is now paired to the codomain, it's not uniquely paired. It's having one, it's having another one there. This one is not mapping. It's not accepted. So both this and this are not acceptable. So now you might be asking, so are they not the same? Here, they're not. Because now for this one here, A is paired to 1, B is paired to 2, D is paired to 2, all right? It's not the other way around, where D is paired to 2 and 3. So they are uniquely paired to at least one element inside the codomain. But for here, A is paired to 1, the same A from the domain now wants to go and marry another one. Why? Be satisfied with 1. So that's why. So that's the reason. Okay, Israel. Yes.
Yeah, just to clarify. So if you are reading the image or range for the one that has 2 elements in the domain paired to 1 element in the codomain, do you have to repeat that number that both of them are paired to, or you just write it as it is, as in the one we
No,
have that has 1, 2, 3 only?
Yeah, 1, 2, 3.
Okay.
Yeah. 1, 2, 3. Okay. So now this is the relation to mapping. Every element of the domain has an image in the codomain. Every element of the domain is uniquely paired to an image in the codomain. So they are uniquely paired. So 2 or 3, you can agree that 2 or 3 more cars, for instance, can have the same weight. All right. So it's just like we have to ensure that what is in the domain is paired to what is in the codomain. You must understand this concept before we move into types of mapping, which is 1-1, onto, bijective, and composition of mapping. So do you have any question here? Okay, so we're good. All right, so now, meanwhile, in here, in our class, our professor told us about the function. He told us how we actually write the function, the elements, and all that. He also told us about the range. The only thing is, it wasn't deep enough, to just let us know what is going on within that function. So probably that's what got a lot of people confused, because it wasn't so deep. All right. But now you understand range, you understand that mapping aspect, what is mapping and what is not mapping. So if you look at this is an acceptable map, right? The map is acceptable in this question, in this example, because everything in the domain here is uniquely paired with an element in the codomain, right?
Someone says she has a question.
Oh, yes. Yes. What's your question? Hope this video will be made. Okay, so well, why can't C be paired to 3? Then D, where is it? Oh, you mean in this equation here? This one here? Is this what you mean, Amina?
No, I mean the first one.
The first one.
That
Okay,
was
here, right?
correct. Yes, yes. Since B is paired to 2 and the same 2 is paired to D, why can't C be paired to the 3 and D?
C is uniquely, okay, this is C. Let me put C's arrow here so you get it. This is C. C is paired mainly to 3 according to the mapping that image they gave to us, while D is going straight to 2 and B is going straight to 2. Now you said, why can't C be paired to 3? C can be paired to 3, but not D. That's not going to be acceptable. Okay, because D is already paired to 2. Do you understand? So two of the elements in the domain can share an element in the codomain. You get, but two of the elements in the codomain cannot share an element in the domain, just like this. This one now, 2 elements, 1 and 3 sharing A. No, that's incorrect. This one now, the elements here are not uniquely paired. That's also incorrect. So the element has to be uniquely paired. Yes, Genevieve.
Oh, I think what she's asking is it a must that B and D is going to be paired with 2? Can't any other element be paired with 2 and D?
Okay. Yes, it can. They can represent it in the other way. We can represent it like this. Can be represented like this. So we can say, and D is also uniquely paired to C. I'll just remove this one. Still acceptable.
Yes, that's what I was asking. Okay.
Yeah, it's still acceptable because it's still uniquely paired to an element in the codomain. All right. So, yes, now we can move into types of mapping. All right, let's go into types. So, types of mapping. Okay. So now for types of mapping here, the first one we have is what we call one-to-one. We call it injective. And since you have a clear understanding of the first part, you understand all this. So we have one-to-one mapping, injective. Now, an injective mapping, when it's said to be, a mapping is said to be injective when elements in the domain are uniquely paired to elements in the codomain, or if no element in the codomain corresponds to more than one element in the domain. What do I mean? Look at this now. This is an example of injective mapping. This elements here are uniquely paired to elements here. That's injective. This is also an example of injective mapping. Elements in the domain are uniquely paired with elements in the codomain. That's also an example of surjective mapping, injective mapping. That's one-to-one. So one-to-one, yeah, uniquely paired. Okay. Now we have another type of mapping called surjective, and I'll just be using the examples above to explain everything. So we have what we call surjective, which is actually known as onto mapping. So a mapping is said to be surjective if every element of the codomain is an image. For instance, what do we mean by that? So let me, you know what? Let me just put this here. Let me put it here. Injective when elements are uniquely paired. When elements are uniquely paired to a codomain. All right, then let me put another one here. So we can take note of that. Surjective, if elements of the codomain is an image. All right, so what do we mean by if elements of the codomain is an image? Look at the first example here. The elements of P here is an image of the element of S because everything is uniquely paired. So this is surjective. But look at this second one. This is injective, but it is not surjective. Why? It's not all the elements of K that is uniquely paired to the elements of P. Because of this last lead, 5 here, we can't say that is surjective. So surjective is telling us that as long as this is an image to this, it's surjective. But because of there is something lacking, it is not surjective. Okay. Then we have another type of mapping called bijective. Now, bijective is just the combination of both of them. So we have bijective. Yes, King.
So are you saying subjective and injective are the same thing?
No, they're not. Injective. Now for injective, okay, one of the elements of the domain will be paired to the elements of the codomain. That's for injective. All right, if now I'll get to you. The elements of the domain are paired to the elements of the codomain. All right, that is for injective. So injective doesn't care about the 5 here. As long as something is paired, no problem. It's injective, one-to-one. Now for surjective, they must be, all of them must be paired to the domain. So if something is not paired to the domain, it's surjective. It's not surjective.
Okay.
Yeah.
So for injective, it can be paired to any codomain.
Yes. Yes. So that is injective. At least one in the domain is uniquely paired. So it doesn't matter if there are more elements in the codomain. But for surjective, it must be an image. It must be an image like this one, because everything must be paired to something. The set must belong to each other. That's for surjective.
Thank you.
You're welcome. Yes, Ifunaya.
Sorry, my question is basically if the video will be available because you've not addressed it.
Oh yes, I said that at the beginning. It's recorded. The whole class is recorded. Now the problem is, will you have the gigabytes to watch? Because this is going to be like how many hours class? It's a marathon, so it's going to be so long, you know. All right. So
One more
a mapping.
Question.
Yes.
Are we expecting more classes? Yes. Oh, this is the only class.
How do you mean?
Like on more courses.
Oh, this is my little contribution. I'm not a lecturer. I'm a student.
Oh, okay.
Yeah.
Yep.
It's just my little contribution. But if I'm going to host another class, I'll let everyone know as well. So, or you can reach out to me in DM if you need to understand anything. So for bijective, a mapping that is both injective and surjective. that is bijective. Mapping that is both injective and surjective, that is bijective. So so S, so the first example and the second example are bijectives. The first example, I beg you. First example and the second example, they are bijective because you're combining both the injective and the surjective. Now, this is the understanding of the types of mapping. Before we move further, we have what we call the composition of mapping, and then we have what we call identity mapping. But before we move further into that, or constant mapping, I want us to understand, I want us to grasp. Do we understand injective? Do we understand subjective? Do we understand bijective?
No. Just explain bijective a little bit.
All right. So, okay. So for, all right, praise, subjective and bijective. I'll explain that. Now, for subjective, all right, subjective is telling us that it must be an image. This is subjective. The reason why this is subjective is because everything in the codomain is uniquely paired with an element in the domain. Subjective. Now look at this. This is not subjective because there is still an element here that is not uniquely paired to an element in the domain. So it is not subjective. Rather, we can say it is injective. It is injective. Injective states that everything in the domain must be uniquely paired to something in the codomain. So this is injective. A is paired to 1, B to 2, C to 3, and D to 4. It is injective. Yes, you get access to the recording. I'm going to post it. I'll put it in the groups. So I'll post it and put it in the groups. What happened? You want to run away? Don't run. So we're having a long marathon here. At least, don't worry. We'll all leave by, let's say, 5:50. So whichever what we can cover by that time will be good. But I'll see if I can do another one tomorrow. That's if you guys are available. But you know, we can discuss other things and all that. But let's focus here before we go on break, because we'll soon be going on break now. So your data. Hey, all right. Injective, subjective, bijective. Bijective now is a combination of both. All right. So praise and king. Do you understand?
Combination of both in what way?
All right. So combination of both in that this is bijective and this is also bijective, because it can be injective and this one can be subjective. So this one can stand as injective and it can also stand as subjective. So it is bijective. Okay. Now this one can stand as injective, but it cannot stand as subjective. So it is not bijective. Okay. You see that?
Okay.
Yeah, we can schedule stats 111 and physics maybe in the next class. Chidima. It is the same Chidima that did that one Miva. I'll be Miss Queen Miva. All right. So, oh, Chidima was the one that was carrying you up and down everywhere. The one that was doing camera up and down. That man that was moving everywhere. That boy, troublemaker. That was me. Yes, it's me. The one wearing durag. I was the person there. I see get our picture, no worry. So let's go into composition of mapping. Now, this is another interesting part. So, thank you. Composition of mapping. I'm not kidding, no. Let's go into composition of mapping. So let's say the function of f is read such that S is contained in a codomain of T, and the function of G, when you have a function already, G is just like the representation of another function. So we have T to an image of U. Okay, so let's say, thank you. Let's say f to the function, f is representing the function of S to T, and G is also representing the function of T to U. So let it be any function, and we can compose that we can compose. Then we can get it to a mapping as H. So let's say we can use the mapping H to say S can also be equal to U. Don't worry, I'm going to explain this. S is equal to U. So what this means is that what this means is that if we have S to the function of T, so S is mirroring T. Now, P is the domain mirroring U as a codomain, and then S is a domain mirroring U as well. So this one now, this is G function, and this is H function. G function and H function. Don't worry, Aminat will be getting into a break in the next 5 minutes, so you can use that one and relax more, you know? Okay. That's why I'm taking 30 minutes so that we can, you know, refresh. So this is what we call the composition of mapping. Right? And then we have what we call identity mapping. Identity mapping is when all the elements are the same. So let's say the elements of, instead of me having ABC, okay, let's say, instead of me having, which one here is the same? Okay, let me put it this way. So let me remove this 5 now. So instead of me having ABCD, and then here 1, 2, 3, 4, I'll just have ABCD and ABCD as well. So that is called identity mapping. The domain is equal to the codomain. That's identity mapping. Then there is constant mapping. In constant mapping, this is an example of constant mapping, where C and D is connected to 3. C and D is to the function of 3. Okay, I said for identity mapping, King, I said A, B, C, D, and 1, 2, 3, 4. Instead of me having 1, 2, 3, 4 here, for identity, this will just be A, B, C, D again. So A, B, C, D in the domain, A, B, C, D in the codomain. That is called identity mapping. Do you get that? Okay. Then we have what we call constant mapping. In constant mapping is an example of constant mapping is this, where all elements of a domain, all right, it assigns to a single. So let me just give an example here. For instance, let's say we have this, and we have a codomain here. And in this one, we have X, we have Y, and we have C. And here we have T and R and W. Okay, now let's say X is assigned, Y is assigned to R, Z is also assigned to R. See this. Okay. Now, this is what we call constant mapping. They are all assigned, they are all uniquely paired to R. Just like what we had here. It's just that this one, A and B, is not uniquely paired to 3. But here in constant mapping, sorry about that. In constant mapping, they're all assigned to a single element. All right. Then we have what we call the inverse function, and that's what our lecturer was trying to say. For any function f to have an inverse, it must be bijective. So the function must be injective and surjective at the same time.
What is compared to what is connected to one function? What is
okay, a constant. That's a constant mapping. Yeah, constant mapping. So that is constant mapping. All right, so that's it about it. We can now move into, yeah, there are ways where we can move into function. Now let's solve some questions under this. Okay, we have just 2 minutes to break time. So do we understand the introduction, this mapping and functions and what it entails? Okay. All right, so we'll be going on a short break. This is going to be short because this is going to be like our last break, right? I think so. I'll make it just long because it's going to be our last break to 5:50. So we can do the value of a function again to quadratics. Okay. In function class, trust me, you would want to, listen. There are lots of things in function class, and we'll treat it together. Don't worry. We'll treat it together and get into quadratics. Okay. Before going into break, do you have any questions? Any questions there so far? All right, so I'll take that as a no. If there are no questions, Amina, you can go on break now. We have 30 minutes, so you can go on, yeah. Amina wants to run. Idima, yes, you can also go on break. Chidima, let me even show you that picture. So for those of you, some of you must have even seen me because on that Miva Connect, I was the one doing most of the introductions. No fear, no fear. I'm the one doing most of the introductions. Let's see, Miva. Okay. All right, let's see. This is the question here. This is the photo here. So you see this guy at this part here. Let it load. You see this guy here. I was one holding Chidima that side. See me, I was everywhere in that. That is, yes, we'll get into quadratic equation once we finish mapping. Look at me here. And when I had this girl won like this, I just went in. I went to go and celebrate because I was almost everywhere. So yeah, that is me. I'm sure most of you guys, you saw me this thing. Then someone was asking, why do you always tie your hair and all that? This is me and Emmanuel when we're coming in the bus, I think. I don't know if Emmanuel is in this class, but he calls himself. Calls it, I don't know if you are here, Emmanuel. So yeah. I mean, I didn't see me care. Someone was telling me, why do you always cover your hair and all that? This is the reason I tie my hair. Because if I put it out there like that, there are going to be issues. So that's how my hair is long. And people always complain that why is my hair long like that and all. So I used to try and cover my hair so I don't, I don't cause issues because of problem. I don't cause issues. There are many. I say I should not cover it. I'll cover it too. That's why I'm always on the rag. I'll cover it. I beg. Them go catch you for real. Oh yeah, now. Oh, let us enjoy our break. Actually wants to plate my. Don't worry, we'll see. Help me and plate the hair. Oh, yes, oh. But most times I pack it though. I'll just pack it, then I cover it for some events. Okay, so I guess everybody here already know what I do. Even myself, I'm tired of presenting. I think we all know what I do already. So you come and support my ministry. Oh. uh, you know, go toast me. You come and support my ministry. Oh, please. There'll be packages, but I'll communicate that in the next. I'll communicate that in the next class that we're going to have. So we have 24 minutes. Enjoy yourself, relax, stretch. Because after this, the last break. After this, we're moving straight into from functions straight into quadratics, and we end. So I should have made it even 45 minutes, but 30 is okay. So yeah. Oh, Bruno, now you 12
Alpha
a.m.
boss. Alpha boss.
Yeah.
How long you go take for the link to come out?
Let me see. I should have it within an hour or two. It's Google Meet. So yeah.
You know, I dey play drums for my church and I just go rehearsal now.
Oh, okay.
So I'll be watching.
No
Thank
problem.
you.
No problem. You're welcome.
Appreciate you, bro.
You're welcome. So don't worry, I'll put a package for Miva students. Hey, you are in Miva and all that. Okay, if it's the coding, if it's the mathematics or things that deal with calculations and all that, let's there will be a package. You just pay me for the semester, enter my class. We'll be having classes every weekend, Saturday, Sunday. Ask your question.
How much is it? Let me look for the money and pay for next semester.
Yeah, next semester, not this semester. This
How
one,
much? How much? Is it all
uh,
the whole subjects?
Jesus, you,
That is
you
good.
want to kill me.
You said you said every weekend. That's now Saturday and Sundays. Like we can do like 3 Saturday, then 3 on Sunday, or maybe 4 Saturdays, 4 Sundays.
Yeah, that one save day. It can be like that too. That one day, that one day.
How
You
much
can
is
just
it now? Let's look for the money.
pay. Let's do semester round-up fee. Let's
Uh-huh.
semester round-up fee. Just pay 50K.
50,000. Is
Yeah,
that a
now.
last one?
It's too cheap, Abby. I should increase
Is
it.
that no? I think is that your last price? Are you not going to go lower?
I've gone lower.
We plenty, oh, we plenty. Come on, money now.
I've gone lower. Okay, how much is your negotiating price?
I don't really have anything in mind though, but I'm just saying in case all of us cannot really afford the 50K. So just put a
It's
reasonable
Don't
amount.
worry. It's flexible payments
Who
within
that
the
person go
entire
talk
semester.
$20? Who talk that $20? Is it okay? Okay, $20 today, okay, 30,000. Is it okay?
We can do this thing. Um, you can spread it across the entire semester. So till till it's time for
Let's
exam.
do $20.
$20. Make it
Yes.
25.
$20, $20, 30,000. You know, say
Make
it dey increase. It depends on the rate. The rate self will give you much money. So
Yes,
they
just yeah, it dey increase, and if you reduce, like now, dollar right now in standard exchange rate is 1,330. If you want to convert to naira, it has reduced from 1,4 to 1,330. So, and I'm like, those earning in dollars now, they are crying because what they were
next
calculating before.
time, next semester, dollar fee rise.
Yeah. That one is possible too. That one is
Let me just
possible.
leave am. Let me just leave am that 20. If the thing rise next semester, we'll pay 20. If it drop, hell, so that if go add 30. If you rise, we'll pay 20.
For semester, for the
Every
semester, pay
semester now.
for the semester, that 50K dey okay now. If you just spread them across, maybe this first month,
No.
you pay like
Oh my God.
next month,
We
you pay like 10.
we many die, my boss.
You no matter now. Now the service I go give each person. So if you anyway we say on in the classroom or weekends, I can put in assignments and then I'm still answering everybody. A task now. A task.
Okay, it's still okay. Let's everybody come to one conclusion first. So I'm not gonna decide for people how much they will pay. And talk with the boss.
That one did.
Okay, thank you.
Welcome. I mean, I hope you've gone for break. Oh. Go and stretch. All right, so we have 10 seconds. Hope you had a wonderful break because, okay. All right, confirm with me if you can see the board. Class has started. Okay. All right. Good. So we're here. Let's deal with functions and let's kill quadratics. And after that, the class is going to end by 5:50. So after that, if you have any further inquiry, questions, you can reach out to me in my DM, and we'll get it there. Actually, though, I do have a demo presentation by 6. That's why I'm ending by 5:50. So, you know, also trying to make ends meet. Let's deal with this. Okay, so we've talked about mapping and functions. We talked about the relations, how we can identify mapping, how we can identify what is mapping and which is accepted and which is not accepted. We talked about the different types of mapping, which is the injective, that's one-to-one. We have the surjective, we have the bijective, which is the combination of both injective and surjective. And we also talked about the composition of mapping, how these different functions, they relate to one another. And then what else? We talked about the functions, introduction to functions and inverse of a function. But we're going to start taking examples first. So we'll start taking examples first. And let's deal with this. So let's consider the mapping that is here. So this, we deal with examples, and after the examples, we move into functions properly. Then we can enter quadratics. Hopefully, we enter quadratics. Okay, so let's consider this. Let's say we have this to be A and this to be B. Okay? And we have a function G. And A has P, Q, P, Q, R, S, T. And B has just 1, 2, and 3. So we can say the question is saying P is paired to 1, Q is also paired to 1. Uniquely, they are paired. R is paired to 2. Uniquely. And then S is paired to 3. And T is also paired to 3. So they're uniquely paired as well. So the question is, what are the elements of the codomain of G? So the codomain of G, what are the elements? Very simple question. So what are the elements of the codomain of G? So G is the function here. We already know what is domain and what is codomain. A is domain and B is codomain. So what are the elements of B? That's what the question is saying. So it says, what are the elements of the codomain of G? That's what it's saying. What are the elements of the codomain of G? So the codomain of G, right? So you just say image as a codomain of G. We have, okay. Yep, but the elements of G for the codomain, which is B, is going to be 1, 2, and 3. 1, 2, 3. That is the set of B. Okay, the question went direct to just tell us list the elements of G, the codomain. So B is the codomain, right? And the elements of that codomain is 1, 2, and 3. Okay, so codomain. Okay, do you understand that? Okay. All right, so it is saying here that consider this mapping A and B, right? A has a set of P, Q, R, S, T, which is the domain, and B has a set of with elements 1, 2, and 3. So it wants us to consider that. Then you can see they are uniquely paired to different elements in the codomain. So the question here is saying, list the elements of the codomain. And the codomain is B. The elements in the codomain are 1, 2, 3. You understand now? Oh, G is the function. So we can write G or we can write F. It's like the function of this mapping, the statement of this mapping. That is what G is. That is what, or you can say F or you can say H. That's what it represents. It's the function of the mapping. That is it. Okay, so let's try another one. Let's say we have, let's try, what if we have something like this? What if 4 was added to this as an element? And it says we should list the codomain of G. So the codomain, the elements of the codomain of G is going to be what? Correct, Israel, same answer. So yeah, same answer. It's going to be 1, 2, 3. But now let me ask, what is the image of G? Okay, hold on. Hold on. All right, there was a mix up there. The codomain has elements of 1, 2, 3, 4. The image represents things that are uniquely paired. So the image is meant to be 1, 2, 3 that are uniquely paired, and then the codomain or the elements of the codomain are 1, 2, 3, 4. So the image is like what is paired according to our knowledge. What is paired? So that same answer, it's the mix-up, yeah. So I thought you were referring to the image. So the image is what is paired. 1 is uniquely paired, 2 is uniquely paired, 3 is uniquely paired. That is the image. The elements here are 1, 2, 3, 4. That's the element in the codomain. While the image of the codomain is what is uniquely paired. That's the image of the codomain. Okay, so we have more questions. Now, this time around, we're going to be dealing with functions. Yep. Find, question here says, find the domain of, okay, let me put it there. Oh, okay. I mean, the correct answer to the image of G, if it's this question we're dealing with, the image of the codomain, the image of G is going to be 1, 2, 3, because it is paired. But the element of the codomain will be 1, 2, 3, 4. That's for the second question. I just included 4 to give us a brain teaser. Okay. But the main question didn't include 4. I was just trying to. I was trying to explain that. Sorry. Let's find the domain. Do you understand, Amina? Find the domain of. Okay. So find the domain here. Find the domain of, let's say, F and f is read as x. The function of f is x such that x is assigned to x squared plus 6. Now we start our calculations. If the range, okay, if the range of f is, say the range of f is, let's put this here, 6, 7, 10, 15. So the range of f is 6, 7, 10, and 15. So it wants us to find the domain. So the first thing you want to do here, what you do is you calculate it with the range of 6. You see all this range here is telling us one thing, right? It means that we're equating. Look at this range that is given to us in the question. Take a look at it. When you want to find the domain, you have to equate the codomain, all right, to whatever the domain is saying, just like what is here. It has to mirror the domain, right? So now they are telling us that this domain, the range is from 6, 7, 10, and 15, meaning that I can say for range 6, okay, that means wherever I'm going to equate x squared plus 6 to be equal to 6, it's going to have to mirror that domain to be equal to 6. And then I solve for x. For range 7, it's going to be x squared plus 6 equal to 7. And then I find x. For range 10, sorry, see my handwriting there. For range 10, it's going to be x squared plus 6, that's the equation, equal to 10. What we're doing here is that we're mirroring. So x squared plus 6, is meant to be equated to the domain. So the domain has a range now. This is a range. So we start calculating. Same thing with 15. For range 15, so let's do this one first. For range 6, so what we have, we're trying to find the domain, right? So this would be x squared equals, let's make x subject of formula. We move 6 to the other side. So this becomes 6 minus 6. Then x squared equals 0. And in order for you to remove the square in any number, you need to find the square root first. If it is cube, you will find the cube root of both sides, right? So you have the cube root of both sides. And then you can now say x can stand on its own. And the square root of 0 is 0. So x equals 0 for range 6. Okay, so we have our first domain to be 0. Okay, that is good. That is good. Remember, there is always, whenever you introduce a square root, there's always a plus and minus behind it. We're not going to include plus and minus to 0. All right. So we have, yes, Chukwemeka. So here we have x squared. Let's equate. This is going to be 7 minus 6. So we have x squared equals 1. Remove the square by rooting both sides. Remember, you introduce your plus and minus. Root 1. So here, x equals square root of 1 is 1. So we have plus 1 or negative 1. Yeah, or negative 1. Remember, you introduce your plus and minus when you're putting in the square root. So 1 is a positive, 1 is a negative. So plus 1 or negative 1. Okay. Same thing we do here. So 0, 1, 2, 3, or you can say negative 3, negative 2, negative 1, and 0. that's going to be, that's, you can put that or put the other side. That's going to be our domain set. So x squared, this will be equals 10. Take 6 to the other side. Minus 6. So this is x squared equals 4. And let us remove the square. We root both sides. So that's going to be the square root of 4. And x is equal to square root of 4 is 2. So we have plus 2 and negative 2. Then for range 15, we have x squared plus 6 equals 15. And then we take this to the other side. And so we have x squared equals 15 minus 6. And this is going to give us 9. And then we remove the square. So we have x equals to plus or minus, get root 9. And so x is going to be equal to positive 3 or negative 3. So yes, you're correct. The set of the domain, or the domain set here, is going to be equal to, our domain set here will be equal to what? We have 0, 1, 2, 3. Or you can say the domain set will be, that's negative 3, negative 2, negative 1, and 0. You might be wondering, why did I state the negative, bigger negatives first? Because of the number line. Remember, when we have a number line, this belongs to negative. It progresses from the left to right. And this belongs to x. So if this is 0, we have negative numbers here, and we have positive numbers here. So if you are traveling along, you will state the negative numbers first before you state the positive numbers. So that's how it is. So do you have any questions? Chukwuemeka, what is going on? Do you have any questions? Any at all? Are we all clear on that? Okay, good. All right, so that's how we get the range. Easy, right? Okay, let's try another one. Let's say we have, let's try another one here. Let's say we have, put it here. Let the function f be a set of real numbers. Let it be defined by f. So you're having two answers, Fatima. You're going to have two answers. Okay, so it depends on what they give you in the option. If they give you the positive answers, you pick, but they won't give you two answers. All right, they won't give you two answers at once in the option. Right? So, and then we have x squared. We have x squared minus x minus 2. We're getting into quadratic right now. So, but don't worry. So this is directed to r, defined by, the function f is defined by, function f is defined by x squared minus x minus 2. So where equals, okay, negative 1. This is how they define the set. And 11. This is the set. And arrow is the set of real numbers. and they want us to find the range of f. Okay, R, set of real numbers, find the range of f. Let's find the range of the function f. Set of real numbers, find the range of f. Okay, let me just use type because this my handwriting is not here. Find the range of f. Let's find the range of function f. Right, so what do we do? They've already given us the function. They said here that the function is what? The function of f here. The function of f here relating to x is what? They said it is what? X squared minus x minus 2. That's what they told us. And now they're telling us that we have a range of -1, 0, 2, 5, and 11. So we're going to start taking it as -1 down like that. So now here, they put it here that the function f, look at this question, the function f is w, which is the set of these numbers, is mirroring r, which is the set of real numbers. And function of f is telling us that this is the equation that relates to f. So this is what f means, and this is what it represents. Now we have, okay, someone got 0, -2, 0, 18, 108. Yes, that is correct. So since we have that, what we're going to do here is we already have the function of x, right, to be equal to this. Since the function of x is here, we represent that function with the set. We represent the function with the set. Now, don't get it twisted or don't get it confused. The other one was x is mirroring x squared plus 6, the equation. This one is the equation itself. Look at this other side here. This one was mirroring it. That's why we had to equate. We didn't represent. We equated because x is telling us it is equal to this. Here is different. The function itself is the equation. So that means wherever we see x, we impute the set and the range of numbers. So we test it for -1. So we just impute -1 all squared minus -1, then -2. So we try -1 first, and then we try 0 second. We test everything. So this is going to be 0 squared minus 0, then -2. And then we try the function of 2. So put it inside there again. This will be, sorry, put it inside there again. This will be 2 squared minus 2. We're in mapping and functions. Still functions. We've gotten into functions. Minus 2. Where are you lost? We're still under functions. So where are you lost? What part? Okay. So let's rewind. Is it the first example or the second one? The second. All right. So this is the second question. It says, let the function f be such that w mirrors r. That means it's giving us this kind of thing. Like this now, x. So it is saying w mirrors r. We can say w equals to r, that kind of thing. So it says be defined by the function f is what? X squared minus x minus 2. And it gave us a set of w, where w is equal to -1, 0, 2, 5, and 11. and R is a set of real numbers. Now it's telling us to find the range of F. Well, here we're looking for the range of F. Okay. Here we were looking for the domain. So if we're looking for the domain, we equate it to the range. If we're looking for the range, however, we impute the function. Let me say that again. Here we're looking for domain. So we just equate it to the domain. Here now, this is the domain X, and we had an equation like this. So every range we equated to the what? To the domain. So for 6, we're going to equate it to 6. For 7, we equate it to 7, 10, because we're looking for domain. But when we're looking for the range of a function, we impute the values inside that function. So if we have x squared minus x minus 2, we calculate for the range of -1. Anywhere we see x, we put -1. The same thing with 0. Anywhere we test for 0. Anywhere we see 0, we impute 0. Anywhere we see 2, we impute 2. Anywhere we see x, we impute 2. Anywhere we see 5, we impute that for x. Anywhere we see x here is representing 5 now. So anywhere you see x, you impute what? 5. So this becomes 5 squared minus 5 minus 2, according to the equation. Remember, this is the equation we're looking at here. So x is going to represent the range values. For 11 now, anywhere you see 11, anywhere you see x, you impute 11. So this will be 11 squared minus 11 minus 2. Do you understand? Are we clear on that? Okay. So we can now solve it. -1 squared is 1. -1 is 1. That is 1 plus 1. Then minus 2. That is 2 minus 2. This is 0. And so we just start to calculate. This is going to be 0, 0 minus 2. That is minus 2, -2. And this 2 squared is 4, minus 2 is 2. This is 0. So we just calculate normally. 25 minus 5 is 20, minus 2. This is 18. And then 11 squared is 121, minus 11. Then minus 2, that is 121 minus 13. This is 108. So we just calculate that. And then our required set for the range of the function will be 0, -2, 0, 18, and that's what it's going to be. So, do we understand that? Let me give us one question. Genevieve in praise, are you clear? All right. Okay. So let's try this. Let's try this one. I'll put it here. Make the domain of F such that X is, don't worry, I'll put that out. I'll complete that question. 1 second. Just want to write everything here. -2, -1, 0, and 1. Find its range. find its range. All right, so what this question is saying, if the domain of the function f is read such that x belongs to this as x squared minus 2. So the domain of the function f is x assigned to x squared minus 2 and is negative 2, negative 1, 0, and 1. Find its range. So we're looking for the range. So that means we're going to represent x with whatever range is here. So can we do that? Let's get the answer. Just attempt for like 60 seconds. So let's attempt. So we're finding the range. Let's attempt. Okay, so someone got 0, negative 1, negative 2, and negative 1. Okay, let's see. Please, you write it according to how it is given. Don't rearrange. Let's see others. Let's see others. And yes, let me make something clear. All right, 1 minute is over. Okay, so let me make something clear here. If we're seeing 2 sets here, just the question I think Israel asked when we started this. If we're seeing 2 sets here that are identical, we can as well just impute it as, according to number line, negative 2 comes first, then 0, then we have 18, and then we have 108. Arrange it according to your number line. So some people got negative 2, negative 1, and 2. Okay, that is correct. So you're all correct. Chidebere, you're correct. Fatima, you're correct. John, you're correct. Okay, negative 2, negative. So negative 1 and negative 1 will stand together. Let's do it together. So we're looking for range, right? So because we're looking for range, not domain, we're not equating. We'll just find a function of x. So wherever x is, we impute it in that equation. So this is x squared minus 2. We're looking for range. Let's find the range. So this is going to be, the first range is negative 2. And so we just impute negative 2 squared minus 2. The second range here is negative 1. So we just impute negative 1 squared as x minus 2. Sorry. Like that. We keep going like that. The other one is 0. This is how to find range. So we have 0 squared minus 2. And then we have 1. And this will be 1 squared minus 2. So we can now solve. So negative 2 squared is 4. 4 minus 2 is 2. Negative 1 squared is 1. 1 minus 2 is negative 1. 0 squared is 0. So 0 minus 2 is minus 2. And 1 squared is 1. And 1 minus 2 is negative 1. So I can see negative 1 and negative 1 on my pen. So the range of set here will be, start with your number line, negative 2, negative 1. They are both going to appear as 1 in the set. Negative 1, and then we have 2. Okay, so just remember. All right, any questions? Okay, any questions? All right, so let's move on. All right, fast forward to this. Genevieve, why did you say ah? What happened?
It's because this formula I didn't know that it was supposed to be x equals to s square minus 2. I was not calculating with just s square minus 2. Please, can you be circling the formula in order not to confuse me,
Okay,
please?
you mean this?
Yes, I didn't know that I was supposed to use this x to x square minus 2. And I went to use only x square minus 2.
X squared. Yeah, it's x squared minus 2 we're using.
Yeah, that's what I'm saying. That this I didn't know that this other x was included. Please, can you like next time circle it so that we know what you're calculating with, please? Thank
Okay, the functions. All right, all right.
you.
No problem.
Thank you.
You're welcome. So, that is how to find domain, and that is how to find range. So for range, you just represent. Okay, for domain, you equate. This is for domain. We equated to the set of range numbers given to us. And this is how to find range. We represent, we just put a function of x, and wherever we see x, we impute. So that's the difference between both of them. Okay, so there's also ways to determine injectivity and surjectivity. Okay, 1 second. But let's move into function itself. For some time, let's move into functions. So the value of a function. Boom. Welcome to functions. Please, do we have any questions here? Oh, yeah. They'll give you the formula to use when you're dealing with it. For any questions under this, they will tell you what they need you to represent. Okay. Functions. So now, a function takes another value when the function is redefined. For example, let's say we have, for example, let's say if fx is equal to 2x plus 1, okay? Let's say fx is equal to 2x plus 1, and it says find f to the function of 3x. So that means wherever we see x, we impute what? 3x. That's what it means. If the function is the function of 2, it means wherever we see x, we impute what? 2. And then we solve the equation. So this becomes 2 parenthesis 3x. Oh, this is 2x, right? So this already have. So this is 2 parenthesis 3x plus 1. And this will give us 6x plus 1. And that's it. So for the function of 2, we just represent. So this becomes 2 parenthesis 2 plus 1. 2 parenthesis 2 is 4 plus 1, and that is 5. All right. So if we have a function, see, function is quite easy. Huh? If we have a function of, let's say, function of x such that telling us 10x minus 3, and it says we should find a function of 2. So what we do is we just represent. So this is going to be, wherever we see x, we input 2. So the function of 2, the function of 2 now will be what? 10 parenthesis 2 minus 3, and that is 20 minus 3. That's equal to what? 17. And that's how we deal with functions. Quite easy. So functions actually quite easy. Very, very easy. So what if we have a function like this? You have to simplify functions sometimes. What if we have a function of if, take this for instance, if the function of x minus 4, okay, is defined as x squared plus 2x plus 3, and it asks us to find, and we're asked to find f to the function of 2. Now this is quite different, right? Since we're asked to find x to the function of 2, have you seen the function? The function here is not just ordinary fx that we have. Function here is x minus 4. So first of all, we have to make it just x. Let it just be x. So we'll bring that function down. Now, we want to make you just be x so we can go ahead with our equation. So we'll bring that function down and we'll bring what it's meant to represent. So equal to 2. And we solve for x first. So this becomes 2 plus 4, and then x equals 6. You see that? So now we can now continue our equation and say, okay, we've gotten that to be 6. So this will now read as function of 6 to be equal to, wherever you see x, you impute 6. So this will be 6 squared plus 2 parenthesis 6 plus 3, according to the question. And then you can solve it as 36 plus 12 plus 3, and you have 51. So that's actually how you can define functions, right? Just make sure you represent and ensure that what you're doing is, you're just representing correctly. Okay, that is on that. Then we have what we call the composition of function. So before I go into the composition of function, or the inverse of a function, after composition is inverse. But I will take inverse of a function because that's actually what he gave to us according to this. So all this explanation is just for you to understand mapping and function itself in this part. All the explanation is for you to understand mapping and function itself. So we're going to treat inverse of a function, and so we'll be clear with this. Okay, so that's the last part thing he touched. Our professor, he touched inverse of a function. So let's treat that. Any questions before we go into inverse? Any questions? Yes, Jen.
Please, there was one equation that you solved that you said f, like the function is 3x, but I didn't see. Please, can you go back to that equation? Let me see something. Yes, this you said f is equals to 3x, and here you said 2 bracket 3s. What? Okay. Sorry, my bad. I get it. Because this s is representing this 3x, right? This is
Yes, that is
2x.
correct.
This x is representing this 3x.
Yes.
Yes.
Whatever is here, you You put that from, you replace it with the function.
Okay, I understood now. Thank you.
All right, you're welcome. Okay, so yeah, let's go into inverse of a function, and from there we dive into quadratics. A very interesting topic. All right, so inverse of a function. Say if y is equal to, let's say the function of, let's say we have a function of fx. Let me put a topic here. This is the last part on that function, so I suppose we will have a clear understanding of mapping and clear understanding of functions and sets as well. So let's say we have a function. Let's say y is a function of x. So the inverse of the function of x, inverse of a function is going to be f to the power of -1. This is the meaning of inverse. So what this means is that we solve the equation f to the function of x for x, but it will be in terms of y, then later change y to x. Don't worry, don't worry. We'll take it one step at a time. There are examples that I will show you so you understand the inverse of a function clearly. Okay, so let's say we have, let me put out a question now so we can jump right into it. So let's say the function f over the set of real numbers is defined by, let's say this is defined by a function of x equal to 1 over 2 x, then minus 3. And it wants us to find the inverse of the function of x. Find the inverse of the function of x. So to do this now, we already know that the function of x here is equal to what? 1 over 2 x minus 3. That's the function of x. So what we do here is very simple. We just introduce y. We say let y be equal to that equation, or you can represent it with any other variable of your choice. Let it be equal to what this function is saying. Okay, so let y be equal to 1 over 2x minus 3. And so now what we're going to do is that we now make x the subject of formula. So let me say let y. So we make x subject of formula. This becomes, if we're making x subject of formula, it means we want x to just stand on its own. So anything that doesn't belong to x, we'll first of all move it to the other side. So this becomes y plus 3 equals 1 over 2x. 1 over 2x is the same thing as 1 times x is x, right? So it's the same thing as x over 2. So we can have y plus 3. This is pure maths now. Equals x over 2. And then we can say we cross multiply. So x times whatever, the fraction of a whole number is always 1. So x times 1 equals 2 times y plus 3. Then we distribute, or we open the brackets like what we say in Nigeria. X will be equal to, this is 2y plus 6. Okay, x is equal to 2y plus 6. So now, before you expand, or before you go ahead, instead of you writing this as y, you then flip it back. Remember what I said, that solve the equation y to fx in terms of x, of in terms of y, then you later change y to x. So wherever we have y here, instead of expanding, when we get our final answer at this level here, x equals 2 parentheses y plus 3. After we've gotten x, what we're going to do here is we just replace y back with x. So this becomes 2 parentheses x plus 3. And the x that we looked for here becomes the inverse of the function x. So replace this big daddy back to x and we get our function. Then you can say 2x plus 6. Yes. Oh chim, praise, praise, praise. Don't worry. We'll do another one so you understand. Okay. Okay, ask your question. Ask in which part. All right, let me do it again. Let me do it again. So let's focus on the question. This is the question. Focus on this. I'll solve it again. Focus on this question. Huh? Now it says fx, right, equals 1 over 2 x minus 3, right? And it wants us to find the function of the inverse of the function x. Okay, this is the question now. So we now know that fx, according to the question, fx is normally 1 over 2 x minus 3, right? So what we do here, we just represent fx as y. First of all, introduce y. When you want to solve inverse, introduce your y. So y becomes like the oga, then 1 over 2 x minus 3. So that is step 1. Step 1, introduce y for fx. So step 2 now will be to solve for x. So now we solve for x, we make x the subject of formula. We solve for x, make x subject of formula. So what we're going to do here is we start making a subject of formula. This minus 3, we don't need it, right? Move it to the other side. So this becomes y plus 3 equals 1 over 2 x. Because you remember, when we're moving across the equality sign, the sign changes, right? So minus 3 becomes plus 3. Then this becomes y plus 3. 1 times x is x. So we have x over 2. And then using cross product, cross multiplication, x will be equals to 2 times what? Y plus 3. Like this is our normal math now. Do you understand this part?
Sorry, please. Is it a must that we are going to like take 3 to the other side? Why can't we take y to the other side?
Because it's x we're looking for, not y.
Okay.
We're looking for x. So anything that doesn't concern x, we push it away. And anything multiplied to x or having a fraction of x, we find a way to just remove it by cross multiplication or dividing both sides. You know, we just have to make x stand on its own.
Okay.
So now that we found x, what you now do is you now replace the x that you found to be the function. And the y that is there, instead of you writing y, you just replace it as x. You put it back as x. So now this one is now the inverse of the function. Y changed to x, x changed to inverse. That's what you do. So step 3, introduce your inverse. For your inverse. You see that? So we just replace it. We just replace it. Okay. We replace it. Any question? All right. We are good to go. So before we move into quadratics, just have a few minutes. Before we move into quadratics, I'm going to just ask one question here for the inverse of a function. Right? 1 second. So I can see what actually caused the problem here. I don't even understand what this professor is writing in this place. Okay, I think this is meant to be f raised to -1 x as the function. Then this would be x minus 1. Yeah, I think that's what it's writing there. Not f minus 1x. That should have been a typo. Yeah, that would get people confused though. Well, anyways, let's solve this. Let's solve this and then we'll move to quadratics. So let's say we have if f x is mirroring to x plus 1 or to x minus 1, where x is a real number. I need something more technical. So let's, okay. Find x for which fx is equal to f. Let me start imputing. So this one is mirroring this. This is the formula. 2x minus 1. Then we have f is power -1. And then x is asking us to find the inverse of that. So remember, this is the formula. All right. If f x is equal to 2x minus 1, 2x minus 1 is the formula. So the hint is make your y equals to 2x minus 1, solve for x, and then impute it back. Then you find your inverse. Okay. So it says find the value of x for which fx is equal to this. So let's find the value of x. First of all, I want you to find the inverse. What is going to be the inverse of the equation? It's work for you. Yes. So it's work for you. Just you can use 60 seconds to attempt. So we can move into quadratics now. So, sorry, remember the question. Okay, someone has a question. So remember the question is saying f to the power of x is equal to the inverse of f, right? Then the inverse of the function of x. So if we find the function of x, we'll use the function of x normally and equate it so that we can get our x. So let's say I find the function here. Whatever my function, let's say my function is p. I already know that my fx normally is x minus 1. So if I found my inverse is p, then I'll use it to find x. So someone said x equals 1, right? That is correct. So I'm waiting for another person. Any other person? 2x, 2 into parentheses, x plus 1. Okay, let's solve that together. All right, let's do it together. Let's do it together, guys. All right, so let's say we have, so first of all, I know that the function of x is given as what? 2 minus 1. And the function of x is given as 2x minus 1. Okay, 1 second, Israel. Let's do it together. Watch the steps so you can know what part you missed. So I want to find the inverse first, right? If I can find the inverse, I will equate the function of x to the inverse. So let's find the inverse. So my inverse now is going to, I'll introduce y to find the inverse. Okay, and then I have 2x, then I solve for x. First step, introduce y for fx. Second step, solve for x, right? So I solve for x. So this becomes y plus 1. Move 1 to the other side because it's not needed. Equal to 2x. And then 2x. To get rid of the 2, I have to divide both sides by 2. Normal math, right? So x now is equal to what? Y plus 1. Y plus 1 over 2. Now, where this x is, I'll just replace it as my what? As my inverse of x. That's step 3, right? And where y is, I replace it as what? As x. So I have x plus 1 over 2. So I found the inverse of the equation. The inverse of x, function of x, is x plus 1 over 2. That side is correct, Israel. So do we get that? We found the inverse to be x plus 1 over 2. But we're not done. If you got to this part, congratulations. But we're not done. The question now said that find x for which fx is equal to the inverse. So this is saying fx is equal to the inverse of x. So if that is saying fx is equal to the inverse of x, so what is fx normally? According to the equation, fx is 2x minus 1 equal to the inverse of the function. What we found was x plus 1 over 2. And now the question says we should find x if this is equal to this. Look at it here. Find x for which this is equal to this. So now we equate and then we find. So I can cross multiply. When you have a whole number, just know that the fraction of every whole number is over 1. So this is going to give me x plus 1 equal to 2 parentheses 2 times 2x minus 1. And so I have x plus 1 equal 4x minus 2. So I collect like terms. Whatever is x, I bring it to one side. Whatever is not x, I take it to the other side. So, 1 second. Yeah, so here I'm going to have 1 plus 2 now I move 2 to the other side, and then I'm bringing x to this other side. So this becomes 4x minus x. And this is 3 equals 4x minus x is 3x. Divide both sides by 3 so that x can stand on its own. And x is equal to 1. My voice is already croaky. I'm already getting... All right. So we've found x. So if you got to this part, it means that you understand finding the functions, the inverse of a function. The other side was to find x, which if you got here too, congratulations. Well, if you did this, it means you found the inverse of the function, and that is great. It means you understand the concept. So, but if you didn't get there, you can check the steps again and see which part you missed. All right, do we have any questions? Any questions? Okay, so let us deal with quadratic equation. That's the last part or the last class. Yeah, it's good when you have examples. Examples are going to really, open your mind. It won't be confusing, but if they just combine everything. So quadratic equation. So apparently we're in this is week 3 already. I guess, yep. Sets, quadratic, theory of quadratics, that's week 3 already, I'm guessing. So if you made it to this class and you're here, congratulations, you did well. You've done very well. You stayed for the marathon. Wow. You stayed with Wakama for that marathon. That's crazy. You guys are strong. Oh, we have only 12 people in the call. So that means some people gave up. Yeah. So while some went for their other activities. Now, whenever you're dealing with quadratic equations, you should understand that a quadratic equation or function is noted by the highest power of 2 among others. What do I mean? Highest power of 2. It has a 2-degree polynomial. This is the general equation of a quadratic equation. This is what we call the general equation of a quadratic function or quadratic equation. Now you see the highest degree. This is a 2-degree polynomial. We need logarithm. Yeah. Logarithm can also be broken down. There are easy steps. This is a 2-degree. This is 2-degree polynomial. That's what we call it. 2-degree polynomial. And let's say this. So in a quadratic equation, you should be able to determine which one is the coefficients of all the equations that we have here. You determine the coefficient of all the equations we have. So let me put in different equations. You tell me the coefficient. You tell me what is A, what is B, and what is C. You can see they all look alike. You're having 2-degree polynomial. That's x squared plus 3. Having 2-degree polynomial. All right. So here now, tell me, A is always the coefficient of the highest degree. B is the coefficient of x. C is the constant. So in the first part, what is A? what is B, and what is C? Yes, they allow casio calculators in the exam hall. It's a non-programmable calculator, so we can take it. Right, so what is A, what is B, and what is C? According to what we have. It's soft. So yes, what is A? Anybody wants to help us? A is the coefficient.
A is the
Yeah,
coefficient of x squared.
yeah,
B is the coefficient of x, and C is the constant.
very good. C is the constant, but when we're dealing with this, remember, when I say coefficient, I mean what is at the back of. So A is at the back of, what is at the back of x squared? X squared is standing on its own, so it's just 1. Thank you, John. That is 1. And then the coefficient of x here, that is B. B is just 3 here. And C, which is the constant, is 10. You're going to need it when you're applying your formulas, calculating quadratic equation. You need to know. Now, A here is 7. B here is, there is a minus, so you call it -1. That's -1, not just 1. And then C is -13. That's a minus. There's a minus, don't forget the signs. A here is 19. We don't have a B, so B is equal to 0 here. And then C is equal to 3. You see that? A in this part here is equal to, there's a minus, so that is going to be -1. B is equal to 0, we don't have a B, and C is equal to 14. While here, A is equal to just 1. Whatever is behind a number that is a variable standing on its own, it's just 1. B is 0, and C is 0. So that's introduction to quadratic. Okay, introduction to quadratic equations. Let me clean out this, illustrations. So we have various methods of solving quadratic equation. We have the factorization, we have the completing the square, and we have the graphical method. Let me see something. So, 1 second. We have the factorization method, we have the completing the square, and we have the formula method. So those are the various ways of actually dealing with quadratic equations. Do you have any question in this? Any questions? No questions. All right. So I'm sure we have a clear understanding of our linear inequality. So just in case you're asked of linear inequalities, inequality that's a less than, greater than, number line, all those things were explained in sets. And yeah, we can deal with our question like that. Okay, so there are other things we can touch in quadratics, but for now, welcome to quadratics. I think this is where we have to draw the curtain. It's already 5 to 6, so and do we have any questions so far? Throw up some questions. Okay. Let me put in some questions here. You mean questions in quadratic? We just started quadratic. For tomorrow. For tomorrow. Wow. Quadratic. Okay. Well, for quadratic, we just started. So let me see. If there will be some questions I can put in. But I'm sure with this now, we are clear on everything here. In the sets and functions. At least for today. Wow, we've done a lot. We've actually done a lot. I'll throw up questions. I think those questions should be in the document I'll also send. Because right now, I need to exit. Okay, so yeah, so you can you can unmute your mic and speak. Say Miva suppose employ. Well, who knows? Maybe I'll be assistant lecturer for Mr. Halloward. Vina. Okay, so I'll be stopping the recording here.